Look up at the night sky on a clear evening, far from city lights, and you'll see a breathtaking tapestry of stars. But what lies beyond them, in the profound emptiness between galaxies? For centuries, we assumed those regions were almost completely dark, vast deserts of nothingness where light barely travels. But what if I told you that the darkness isn't as dark as we thought? Imagine pointing the most powerful telescopes ever built into the deepest cosmic voids and discovering something impossible, a faint, pervasive glow where no light should be. This isn't a plot from a science fiction novel. This is real. Astronomers have detected a mysterious radiance filling the spaces between galaxies, a signal so puzzling that it challenges everything we think we know about the universe. This enigmatic light, known as the intergalactic background light, is one of the greatest mysteries in modern astrophysics. It's not coming from stars or galaxies we can see. It's not leftover radiation from the Big Bang. It's something entirely new, something unexplained. Where is it coming from? What's producing it? Could it be the glow from countless wandering stars cast out from their home galaxies? Or might it be evidence of exotic particles, or even dark matter itself, slowly revealing its presence? Each possibility leads to more questions than answers, pulling us deeper into a cosmic detective story that spans the entire history of the universe. In this video, we're going to journey together into the heart of this mystery. We'll explore how astronomers first detected this elusive signal, why it contradicts our best models of physics, and what it might mean for our understanding of reality itself. From rogue planets drifting in the void to the possibility of entirely new laws of nature, we'll uncover why this faint glow has scientists around the world questioning the foundations of cosmology. So settle in, open your mind, and get ready to explore one of the most thrilling frontiers of human knowledge, a place where the light that shouldn't exist is rewriting the story of the cosmos. But how do you even begin to search for a whisper of light in an ocean of cosmic noise? The story of this discovery is a testament to human ingenuity and the relentless pursuit of the unknown. It started not with a single eureka moment, but through a painstaking process of elimination using some of our most powerful eyes on the sky. The Hubble Space Telescope, orbiting far above our atmosphere's distorting glow, played a pivotal role. Astronomers would point its incredibly sensitive instruments at what seemed to be the darkest, most empty patches of space, imaginable regions between the great galaxy clusters where literally nothing should be. They would take long exposure images, gathering every single photon of light over hours and days. Then the real work began, meticulously subtracting every known source of light. They removed the glare from distant galaxies, the faint smudge of nearby stars, even the scattered light from dust within our own solar system. And when everything that could be identified was digitally erased, something astonishing remained. A faint, ghostly glow persisted, a signal that simply should not be there. This wasn't just a fluke in one observation. The New Horizons spacecraft, famous for its Pluto flyby, provided crucial corroborating evidence from its unique vantage point in the outer solar system. Out there, far from the sun's reflective dust cloud, the background darkness is even deeper and more pure. Its measurements confirmed the same enigmatic signal, ruling out the possibility that this was some kind of instrumental error or local phenomenon. This pervasive light became officially known as the cosmic optical background, a diffuse radiance that blankets the entire sky. Imagine it not as a single source you could point to, but more like a subtle, uniform luminosity that fills the vast expanses between all cosmic structures. It's the visual equivalent of a constant, quiet hum heard in a silent room after you've turned off every appliance you can think of. The implications of this discovery sent ripples of excitement and bewilderment through the astrophysics community. As researcher Dr. Michael Zemkov has described it, this is light from unknown sources, a finding that hints we might be missing entire chapters in our cosmic inventory. Our current models of the universe, which have been so successful in explaining so much, suddenly faced an anomaly they couldn't account for. It's as if you carefully calculated the number of people in a city by counting every house and apartment, only to step outside and see a crowd of people with no homes to go to. This glow suggests there is a population of objects or a physical process operating on a grand scale that our theories have completely overlooked. It forces a fundamental and thrilling question. After centuries of studying the heavens, what else is out there shining in the darkness that we have yet to even imagine? So what exactly is this mysterious light that seems to fill the void? To understand it, we need to first distinguish it from other types of cosmic light with which it's often confused. The intergalactic background light, or IBL for short, is a broad-spectrum, diffuse glow that exists in the spaces between galaxies. It's not the brilliant pinpoint of a star or the concentrated glow of a distant galaxy. Think of it more like a cosmic fog, a faint, almost imperceptible luminosity that permeates the entire universe. This isn't the same as the famous cosmic microwave background, which is the cooled remnant of the Big Bang and is detected as microwave radiation. The IBL is optical light, the kind our eyes can see, and it's coming from sources that are much more recent in the universe's history, yet are completely unknown to us. Measuring this incredibly faint signal is a monumental task of cosmic subtraction. Astronomers start by taking an ultra-deep image of a supposedly empty patch of sky with a powerful space telescope. They then embark on a meticulous process of identifying and digitally removing every single source of light they can possibly account for. This includes the obvious ones like resolved galaxies and stars, but also the more subtle ones, the collective light from galaxies too faint to be seen individually, the faint glow of zodiacal light from dust in our own solar system, and even the airglow from Earth's upper atmosphere for ground-based telescopes. It's like trying to hear a single, quiet instrument in a massive orchestra by carefully silencing every other musician one by one. After all that painstaking work, what remains is a faint, uniform signal that simply won't go away. This residual glow is the intergalactic background light, and its very existence implies that our census of the universe is profoundly incomplete. Why is this seemingly minor detail so crucial to scientists? Because light is a messenger, and this particular signal is carrying a story from across time and space. The intergalactic background light acts as a fossil record, a cumulative archive of all the light-producing events that have ever occurred throughout the history of the cosmos. By analyzing its intensity and properties, astronomers can, in theory, piece together the total history of star formation, the evolution of galaxies, and the reionization of the early universe. It's a direct probe into the universe's energetic past, but here's the catch. The amount of light we're detecting in this background doesn't match the story our current models are telling. The signal is too strong. It's as if we're hearing an echo from a crowd that, according to our records, was only half the size. This discrepancy means the archive contains records of events or objects we haven't yet begun to catalog, pointing us toward secrets about dark matter, the earliest generations of stars, or physics operating beyond our current understanding. The journey to understand this faint cosmic glow isn't a new one. It stretches back through the entire history of astronomy. For as long as humans have looked up at the night sky, we've wondered about the nature of light and darkness in the cosmos. But the specific idea of a pervasive, intergalactic background light truly began to take shape in the mid-20th century, as we finally developed the technology to peer beyond our own atmosphere. With the dawn of the space age and the launch of early observatories above Earth's light-distorting air, astronomers could finally stare into the deepest voids with unprecedented clarity. What they began to suspect was both thrilling and confounding. The universe seemed to be filled with a faint, omnipresent radiance that had no obvious source. Initially, scientists proposed what seemed like the most logical and conservative explanations. Perhaps this faint signal was simply the collective light from countless distant, faint galaxies that were too small and dim for our telescopes to resolve individually. It was a reasonable hypothesis, just as a forest appears as a solid mass of green from a distance. Though it's actually made of individual trees, maybe the cosmos was filled with a sea of ultra-faint dwarf galaxies. Another early theory pointed to intracluster stars, enormous numbers of stars that had been gravitationally ripped from their home galaxies during cosmic collisions and now drifted alone in the vast spaces between galaxy clusters. These orphan stars, it was thought, could collectively produce a low, uniform glow. For a time, these ideas provided a comfortable framework, a way to fit the mystery into the existing understanding of the universe. This comfortable framework, however, began to crack under the weight of new evidence. The pivotal moment arrived in the 1990s with the historic Hubble Deep Field observation. Astronomers pointed the Hubble Space Telescope at a seemingly empty patch of sky for over 100 consecutive hours, gathering the faintest light possible. The resulting image was staggering. It revealed not an empty void, but a universe teeming with thousands of previously unseen galaxies, a breathtaking tapestry of cosmic structure. Surely, scientists thought, this deeper look would account for all the mysterious background light. But when they added up the light from every single one of those galaxies, a frustrating and exciting discrepancy remained. A persistent, unexplained glow was still there, a signal that refused to be explained away by known objects. The mystery wasn't solved, it had just gotten deeper. This pattern of discovery leading to deeper questions has a rich history in cosmology. Decades before the Hubble Deep Field, a brilliant and often overlooked astronomer named Fritz Zwicky was studying the Coma cluster of galaxies. He noticed that the visible mass of the galaxies themselves couldn't account for the gravitational forces holding the cluster together. He famously proposed the existence of Dunkel Materie dark matter, an unseen form of mass that must be influencing the cosmos. Zwicky was grappling with a missing mass puzzle, but the intergalactic background light presents a parallel missing light puzzle. It's as if the universe is showing us two different sides of its hidden nature, one through gravity and the other through light. The historical backdrop of these discoveries shows us that every time we build a better instrument and ask a deeper question, the cosmos reveals another layer of its profound complexity, setting the stage for the revolutionary investigations happening right now. So where is all this mysterious light actually coming from? That is the multi-billion photon question that has physicists and astronomers locked in a fascinating debate. The leading hypothesis points us back to the very beginning of everything. Perhaps this faint, pervasive glow is the collective light from the universe's very first stars, often called population 3 stars. These are thought to be monstrous, short-lived giants, formed from the pristine hydrogen and helium that existed just after the Big Bang. They would have blazed with an incredible intensity and then died in spectacular supernova, seeding the universe with the first heavy elements. But because they existed so long ago, over 13 billion years in the past, their individual light is incredibly redshifted and faint, far beyond the detection capabilities of even our best telescopes today. It's like trying to spot a single, specific candle flame from thousands of miles away on a foggy night. While we can't see them one by one, the theory suggests their combined, ancient light could still be washing over us, a fossilized echo from the cosmic dawn that has been traveling through the expanding universe ever since. Another compelling, though less exotic, idea focuses on the countless stars that have been thrown out of their galactic homes. Throughout the universe's violent history, galaxies frequently collide and interact, and these gravitational tugs of war can fling stars out into the immense voids between galaxies. These celestial nomads, known as rogue stars or intergalactic stars, would forever wander the darkness, burning in isolation. Billions upon billions of these orphan stars could, in principle, create a dim, uniform background light. We have even seen evidence of this phenomenon on a smaller scale. The Hubble telescope has observed a faint glow of such stars within the giant galaxy cluster Abell 1689. The problem is, when astronomers run the numbers, the total amount of light we'd expect from this population of castaways still falls significantly short of the observed signal. It accounts for a piece of the puzzle, but a large piece is still missing. This is where the theories venture into truly speculative and thrilling territory. Some scientists propose that the glow could be a direct signature of dark matter itself. We know this mysterious substance makes up about 85% of all the matter in the universe, but we have only ever detected it through its gravitational pull. What if certain types of hypothetical dark matter particles, like actions or weakly interacting massive particles, could decay or annihilate each other? If that were happening all across the cosmos, these interactions would produce standard photons of light as a byproduct. This would mean the faint glow we're seeing isn't from stars at all, but is literally the universe's dark matter slowly revealing itself through a faint, ethereal radiance. It's an elegant idea that could solve two profound mysteries at once, but it remains highly theoretical, as no experiment has yet confirmed the existence of such particles. Yet another possibility is that our inventory of the universe is simply far more incomplete than we ever imagined. Maybe there exists an entire population of extremely faint, diffuse galaxies that have completely evaded our detection. Or perhaps there are unknown astrophysical processes, some form of energy conversion or particle interaction, that generates light in ways our current physics textbooks don't describe. The stark reality is that when astronomers add up the light from every single star, galaxy, and known source across the entire sky, they are still left with a significant excess. This glaring discrepancy is what makes this mystery so powerful. It isn't a minor accounting error. It's a fundamental challenge to our standard model of cosmology, suggesting that we might be missing entire chapters in the story of the cosmos. The search for the origin of this light is pushing our telescopes to their absolute limits and forcing theorists to dream bigger, reminding us that the universe still holds profound secrets waiting in the darkness. Just when you think this mystery can't get any stranger, it throws another curveball that leaves scientists utterly baffled. We've established there's light where none should be, but its behavior is perhaps even more puzzling than its mere existence. If you were to map this faint, intergalactic glow across the entire sky, from one deep void to the next, you'd expect to see some variation pockets that are slightly brighter and others that are a little dimmer. After all, that's how everything else in the universe is arranged. Galaxies themselves are not scattered randomly. They form a vast cosmic web, clustering into immense filaments and nodes separated by gigantic, empty bubbles. This is the large-scale structure of everything we know. So logic dictates that if this mysterious light is coming from objects associated with that structure, its glow should mirror that same lumpy, clustered pattern. It should trace the outlines of the cosmic web like a faint, glowing fingerprint, but it doesn't, not even close. The most confounding characteristic of this background light is its profound and eerie uniformity. No matter which direction astronomers point their telescopes, whether towards a known supercluster or into the deepest, emptiest void they can find, the intensity of this glow remains virtually identical. It's as smooth and consistent as the static on an old television set tuned to a dead channel. This isn't just a little odd, it's a direct contradiction to one of the most fundamental principles of modern cosmology. The universe, from its very beginnings, has been a story of gravity pulling matter together, creating dense knots and vast empty spaces. For a background light to be so perfectly uniform, it suggests its source operates entirely outside of this gravitational rulebook that has governed the evolution of everything else. This incredible smoothness immediately rules out a whole class of potential explanations. It strongly suggests that the light cannot be coming from any kind of discrete, clumped-up object. If it were produced by a vast population of undetected dwarf galaxies or a sea of rogue stars, we would absolutely expect their collective light to be brighter in the regions where matter is more densely packed along the filaments of the cosmic web, and much fainter in the truly empty voids. The fact that we see no such variation means these objects are either not the source, or if they are distributed in a way that completely defies our understanding of gravity and structure formation. It would be like throwing a handful of sand into the air and watching it spread out into a perfectly smooth, solid sheet instead of falling into a random pile on the ground. The mechanism required for that simply doesn't exist in our current models. So what could possibly create such a perfectly even, all-pervasive glow? The answer likely points to something far more exotic and fundamental than mere stars or galaxies. The uniformity suggests a source that is itself perfectly smooth and evenly distributed across the entire cosmos. One compelling idea is that we are seeing the faint emission from a warm intergalactic medium, a thin, hot gas that permeates all of space. If this gas were heated to temperatures of tens of thousands of degrees by the ultraviolet light from the first galaxies, it could theoretically emit a very faint, very uniform glow. Another, even more mind-bending possibility involves not a gas but a field. Certain theoretical particles, like actions, which are a candidate for dark matter, could theoretically convert into photons in the presence of magnetic fields. If this process is happening everywhere uniformly, it could produce the exact kind of smooth, all-sky glow that we observe. This level of uniformity doesn't just add a new question to the list, it fundamentally changes the nature of the mystery. It's no longer just about finding missing objects, it's about potentially identifying a whole new component of the universe or a new physical process that operates on the largest imaginable scales. The light smoothness hints that its origin is woven into the very fabric of spacetime itself, a constant, humming background process that has been ongoing since the universe was young. This characteristic makes it one of the cleanest and most powerful probes we have for testing the limits of our theories, because any successful explanation must account not only for the light's existence, but for its perfect, profound, and beautiful uniformity. But the plot thickens even further when we get to the numbers, and this is where the mystery transforms from a curious anomaly into a full-blown crisis for our cosmic models. Let's talk about intensity. When you add up the light every single photon we can account for from every star in every galaxy, every glowing nebula, every conceivable known source across the entire electromagnetic spectrum, you arrive at a predicted total. This prediction is based on our incredibly detailed understanding of how stars form, live, and die, and it's a number that has been refined over decades of painstaking observation. Now compare that prediction to the actual, measured intensity of the cosmic optical background, the total amount of light we actually see filling the universe. The two numbers should match. They don't, not even close. The real kicker is that the observed glow isn't just a little bit brighter. It can be up to twice as intense as our best predictions allow for. Think about that for a second. We are literally seeing twice as much light in the universe as we have any right to see based on everything we know. This isn't a minor accounting error you could brush off. Imagine carefully calculating your monthly budget, accounting for every single dollar of income and every known expense, only to find your bank statement shows you have twice as much money as you should. Your first instinct would be to assume you made a math error or that there's been some kind of bank mistake. Astronomers have spent years triple-checking their math and their instruments with that same meticulous skepticism. They've used different telescopes like Hubble and New Horizons, operating in completely different parts of the solar system to rule out local contamination. They've developed increasingly sophisticated software to subtract every last possible glimmer of known light, from the zodiacal light in our solar system to the faintest detectable galaxies. And yet, through every independent analysis, this glaring excess persists. The signal is real. The light is truly there, shining in defiance of our most cherished astrophysical ledgers. So what does this massive overabundance mean? It fundamentally forces us to confront one of two staggering possibilities, both of which are equally thrilling. The first possibility is that our cosmic inventory is catastrophically incomplete. We might be missing an entire population of light-emitting objects. This isn't just about a few hidden stars. It would require a colossal number of sources we've somehow overlooked. Perhaps there are far more of those ultra-faint dwarf galaxies than our models of galaxy formation predict, and they are churning out stars at a rate we didn't think was possible for their size. Or maybe there's an unseen realm of celestial bodies, objects that don't fit our current classifications at all, emitting light through processes we haven't yet discovered. The second possibility is even more radical. The light isn't coming from stars or galaxies at all. It could be the product of entirely new physics. The most tantalizing theory is that we are witnessing the slow decay or annihilation of dark matter particles. If certain hypothetical particles, like actions, were to break down or collide, they could release energy in the form of photons. This process, happening uniformly across the vast emptiness of space, could inject this enormous excess of light into the cosmos. This would mean the glow isn't a sign of missing stars, but the first indirect glimpse of the universe's most dominant yet elusive component. Either scenario, a universe teeming with unseen objects or one humming with the energy of decaying dark matter, would require a profound rewrite of the rules that govern astrophysics and cosmology. The intensity of this light isn't just a measurement. It's a direct challenge, a beacon from the darkness insisting that our story of the universe is still missing its most exciting chapters. And now we arrive at one of the most electrifying possibilities in this entire cosmic detective story. What if this ghostly light is our first real glimpse of dark matter? For decades, scientists have known that the vast majority of matter in the universe is invisible. We can't see it, we can't touch it, but we can observe its powerful gravitational pull as it sculpts galaxies, bends light, and holds the cosmic web together. This mysterious substance, dubbed dark matter, has been the single greatest unsolved puzzle in modern cosmology. We know it's there, but we have absolutely no idea what it's made of. Every attempt to directly detect a dark matter particle here on Earth has come up empty. It's a cosmic presence that has remained utterly silent, communicating only through the force of gravity. That is, until we discovered this unexplained intergalactic glow. The theory is as elegant as it is profound. What if certain types of hypothetical dark matter particles aren't completely stable? Imagine a scenario where these particles, after drifting through the cosmos for eons, occasionally decay or even collide and annihilate one another. According to the laws of physics, such an event would release energy. And one of the most fundamental forms that energy can take is light photons. If this process is happening, even at an incredibly slow rate, across the vast expanses of the universe, it would produce a faint, uniform, and pervasive glow. This would mean the light we're seeing isn't from stars or galaxies at all, but is literally the universe's dark matter slowly revealing itself, not through gravity, but through a faint, ethereal radiance. It would be the first non-gravitational signal from the cosmos's dominant yet hidden component, a whisper finally heard after eons of silence. The leading candidates for this kind of transformative discovery are particles with names that sound like they're from science fiction: Actions and WIMP, which stands for Weakly Interacting Massive Particles. Actions are hypothetical ultra-light particles that were originally proposed to solve a completely different problem in particle physics. They are now a prime candidate for dark matter because they could theoretically flood the universe, behaving as a cold, collisionless fluid. Under the right conditions, particularly in the presence of strong magnetic fields, actions could spontaneously convert into photons, creating the exact kind of diffuse glow we observe. WIMP, on the other hand, are a different class of heavier particles. The idea is that when two WIMP meet, they could annihilate each other in a flash of energy, producing standard particles like electrons and, crucially, photons of light. For years, massive detectors buried deep underground have been searching for the rare recoil of a WIMP bumping into a regular atom. Seeing their potential light signature in space would be an astonishing alternative way to finally catch them. However, this elegant theory immediately runs into a significant problem: tension with existing models. The simplest and most popular versions of these dark matter models don't naturally produce the amount of light we're actually measuring. To explain the observed intensity of the intergalactic glow, the decay or annihilation rate of these particles would have to be far higher than what most theorists find comfortable or natural. It's a classic scientific dilemma. The simplest explanations often don't match the complex reality of the universe. This doesn't kill the idea, but it forces physicists to consider more complex and exotic versions of these theories. Perhaps dark matter isn't made of just one type of particle, but a whole dark sector with its own forces and interactions, much like the complexity we see in the visible world. This would open up a vast and uncharted territory of physics, a hidden world operating parallel to our own. This is why the connection between the intergalactic light and dark matter is so powerful. It represents a potential convergence of two of science's greatest mysteries. Solving one could instantly solve the other. Researchers are now chasing this connection with a multi-pronged attack, using supercomputer simulations to model how different dark matter properties would manifest as a background glow, and comparing those results to the precise measurements from Hubble and New Horizons. Meanwhile, particle physicists are refining their experiments, knowing that a detection in their underground labs could provide the missing piece that explains the light in the sky. The enigmatic glow between galaxies has become a new bridge between the immensely large and the infinitesimally small, between the realm of cosmology and the world of quantum particles. It's a thrilling reminder that the answers to the universe's biggest questions are often hidden in the most subtle of signals, waiting for us to become clever enough to see them. This faint, pervasive glow we've been chasing might be far more than just a modern anomaly. It could be a message from the very dawn of time, a fossilized echo from the universe's violent and spectacular birth. To understand why, we need to rewind the cosmic clock all the way back to a period known as the Cosmic Dark Ages. For hundreds of millions of years after the Big Bang, the universe was a vast black expanse. There were no stars, no galaxies, no sources of light. It was just an expanding, cooling fog of primordial hydrogen and helium gas. Then, slowly, gravity began to pull the densest patches of this gas together, collapsing them into the very first structures. And when the pressure and temperature at the cores of these collapsing clouds became great enough, nuclear fusion ignited. In that moment, the very first star was born, piercing the darkness and ending the cosmic dark ages forever. This epoch, aptly named Cosmic Dawn, was a revolutionary period. Those first stars, known as population 3 stars, were nothing like the stars we see today. They were behemoths, hundreds of times more massive than our Sun, burning ferociously hot and blue, and living short, dramatic lives that ended in colossal supernova explosions. They were the universe's first factories, forging the first heavy elements like carbon, oxygen, and iron in their cores, and then scattering them across space in their violent deaths, seeding the cosmos for the generations of smaller, longer-lived stars that would follow. The light from these primeval giants was intense and transformative. It began the process of reionization, where the energetic ultraviolet radiation from these first stars and early galaxies ripped electrons away from the neutral hydrogen atoms that filled the universe, slowly turning the opaque cosmic fog into the transparent intergalactic medium we see today. This is where our mysterious background light enters the story. The leading hypothesis is that what we are detecting is the integrated, collective glow from that entire first generation of stars and galaxies. Because they are so incredibly distant and their light has been traveling for over 13 billion years, it has been stretched and redshifted, arriving at our telescopes as a faint, diffuse optical and infrared signal. It's the combined whisper of the universe's first light, a fossilized snapshot of creation itself. If this is true, then this glow is the closest we will ever get to directly observing cosmic dawn, offering an unprecedented window into an era that is currently beyond the direct reach of even our most powerful telescopes. However, this elegant story immediately hits a major snag. When cosmologists run sophisticated computer simulations of the early universe, modeling the formation of these first stars based on our understanding of physics, they can predict how much total light this population should have produced. And just like with the modern universe, the numbers don't add up. The amount of fossil light we seem to be detecting is once again significantly more than these models predict. This discrepancy forces us to ask some deeply unsettling questions about our cosmic origin story. Did star formation begin much earlier than we think? Did those first stars form with a different, more efficient kind of brilliance, or were there simply far, far more of them than our theories allow for? The implications are staggering. If the timeline of cosmic dawn needs to be moved earlier, it would mean the universe woke up and got to work forming structures faster than anyone believed possible, compressing hundreds of millions of years of evolution. This would force a dramatic revision of our models for how dark matter and gas behaved in the infant cosmos. Alternatively, if the first stars were fundamentally different, perhaps even more massive and luminous than we've ever conceived, it would rewrite the book on stellar astrophysics before the first chapter was even fully written. This faint, uniform glow is therefore more than just a mystery. It's a direct challenge to the entire narrative we've constructed about how our universe grew from a hot, dense state into the structured cosmos we see today. By studying this ancient light, we aren't just looking for missing objects, we are stress-testing the very story of our origins, and the universe seems to be suggesting we've missed a crucial plot twist. Now let's turn our attention to something a bit more familiar, yet no less mysterious: cosmic dust. We often picture dust as a nuisance here on Earth, but out in the cosmos, it's a fundamental building block. These tiny grains of carbon, silicon, and other elements are forged in the hearts of dying stars and scattered across galaxies by stellar winds and supernova explosions. This interstellar dust is far from inert. It plays a crucial role in the cosmic life cycle. It helps clouds of gas cool down and collapse to form new stars. It clumps together to eventually form planets, and it actively interacts with light. Dust doesn't just block light, it can also absorb it, re-emit it at longer wavelengths, and scatter it in new directions. So, when astronomers detected this unexplained intergalactic glow, a very reasonable first thought was, could this simply be the collective shimmer of countless dust grains floating in the vast emptiness between galaxies? This line of inquiry led scientists to run the numbers, meticulously modeling how much light we should expect from all the known dust in the universe. They tallied the dust within spiral and elliptical galaxies, the dense clouds in stellar nurseries, and even the debris expelled from aging stars. The result was a definitive and surprising conclusion. While this dust contributes to the background light, it falls spectacularly short of accounting for the massive excess we observe. The known populations of dust, even when extrapolated to fill the entire cosmic web, simply cannot produce a signal this bright or this uniform. It's like trying to light up an entire football stadium with a single candle. The scale is just completely wrong. This realization was a major setback for one of the most straightforward explanations, forcing astronomers to confront the fact that this mystery required something beyond the ordinary. Undeterred, some theorists began to explore more exotic possibilities. What if there's a form of dust we haven't discovered yet? The concept of dark dust was proposed: hypothetical particles with unusual properties that could exist in the intergalactic medium. These wouldn't be the familiar silicate or graphite grains we know. They might be composed of something entirely different, perhaps even linked to dark matter itself, with a unique ability to generate or scatter light more efficiently. Another idea considers whether colossal, galaxy-scale collisions or powerful galactic outflows could be launching immense amounts of dust and debris far out into intergalactic space, creating a vast, unseen reservoir of light-scattering material. While intriguing, these speculative theories face their own hurdles. Detailed calculations show that the energy required to distribute enough dust so evenly across such immense voids is practically unimaginable, and no current observational evidence supports the existence of these hypothetical particle types. This leaves us with a profound insight. The dust mystery demonstrates that even the most familiar components of the universe can harbor hidden depths and surprises. We thought we understood cosmic dust, but its inability to explain the glow reveals a gap in our knowledge. It underscores that the intergalactic medium, the space between galaxies, is not a perfect vacuum. It's a complex ecosystem, potentially containing a menagerie of faint, diffuse material that our current telescopes simply cannot resolve. Solving this piece of the puzzle will require a new generation of observatories with unprecedented sensitivity to map this faint debris in all its forms, searching for the missing material that could finally illuminate the source of the light that fills the darkness. Of course, the most natural human response to such a baffling signal is to question not the universe, but the tools we use to observe it. Could this entire mystery be nothing more than a sophisticated illusion, a ghost in the machine created by our own technology? Skeptics have rightly raised this crucial point, suggesting that the glow might be an instrumental artifact, a subtle form of self-deception baked into the complex process of modern astronomy. After all, we are asking these telescopes to perform Herculean tasks, to detect the faintest whispers of light against an overwhelming chorus of noise. The potential for error is immense. It could be stray light, a tiny reflection bouncing around inside the telescope's optics from an unexpected angle. It could be an imperfection in the ultra-sensitive detectors, a persistent thermal noise, or a minute electrical glitch that mimics a real signal. Or perhaps it's not the hardware at all, but the software, a flaw in the immensely complex algorithms used to process the raw data, to calibrate the images, and to subtract all the known sources of light. In a way, hoping for an instrumental error is the most comforting explanation, because it would mean the universe still obeys the rules we've so carefully written for it. This is why the scientific method is so powerful. It builds in its own skepticism and demands independent verification. To rule out these haunting possibilities, astronomers didn't rely on a single instrument. They embarked on a campaign of cross-examination using a fleet of the world's most powerful observatories, each with its own unique strengths and potential weaknesses. The Hubble Space Telescope, observing from Earth orbit, provided the incredibly deep and sharp images that first revealed the anomaly. But to ensure this wasn't some quirk of Hubble's specific location or design, scientists needed a second opinion from a completely different vantage point. They found the perfect witness in the New Horizons spacecraft. By the time it made its measurements, New Horizons was far beyond Pluto, over 4 billion miles from the Sun. At that incredible distance, the solar system is an entirely different place. The cloud of dust that fills the inner solar system, which scatters sunlight to create the zodiacal light that plagues ground-based and near-Earth observations, is virtually non-existent. The sky there is blacker than any black we can experience closer to home. And when New Horizons turned its camera toward the darkness, it saw the same thing Hubble did, that persistent, unexplained glow. This independent confirmation from a second, utterly distinct instrument was the turning point. It transformed the signal from a curious anomaly into a serious astrophysical phenomenon. Yet, the work of subtraction is a painstaking and nuanced art. The most insidious contaminant is zodiacal light, the faint glow of sunlight scattered by countless dust grains orbiting in the plane of our solar system. From Earth, this glow is a significant factor, a diffuse cone of light that can be seen rising from the horizon before dawn or after dusk under perfectly dark skies. For astronomers, it's a foreground fog that must be meticulously modeled and digitally removed. The models for this are incredibly sophisticated, based on maps of the solar system's dust distribution, but they are not perfect. Any tiny error in this subtraction process could leave behind a false residual signal that looks exactly like the mysterious glow. Teams have spent years refining these models, using data from dedicated missions like the Pioneer and New Horizons probes to understand the zodiacal light with unprecedented precision. And still, after applying the most rigorous corrections possible, the signal remains. It's like cleaning a window with the finest cloth over and over again, only to find that a faint, persistent smudge is actually something on the far side of the glass. This ongoing, meticulous debate is not a sign of weakness in the science. It is its greatest strength. That residual uncertainty, however small, is the engine that drives progress. It underscores a profound truth about modern astronomy. Our reach constantly exceeds our grasp. We are building instruments so sensitive that they can detect the faintest imaginable signals, and in doing so, they also detect the faintest imaginable errors. Pushing past this frontier requires a new generation of tools and techniques. It demands space telescopes designed with even more baffling to suppress stray light, detectors cooled to within a fraction of absolute zero to minimize thermal noise, and data processing algorithms powered by machine learning to identify and eliminate subtler forms of contamination than ever before. The mystery of the intergalactic glow, therefore, is as much a story of engineering and data science as it is of cosmology. It's a high-stakes test of our ability to see clearly, and so far, every time we clean our lenses and look again, the universe continues to shine with a light that defies explanation. Perhaps the answer to our cosmic light puzzle isn't something exotic or new, but something incredibly small and incredibly numerous. What if the universe is teeming with countless tiny, faint galaxies that have simply slipped beneath the detection limits of even our most powerful telescopes? This is the compelling premise of the missing galaxies hypothesis. Imagine an ocean so vast that we've only ever noticed the giant whales and the large ships sailing on its surface, while beneath the waves exists an entire ecosystem of tiny, glowing plankton, each one too small to see individually, but together creating a brilliant, uniform luminescence that lights up the entire sea. In this analogy, the known galaxies are the whales and ships, and the mysterious intergalactic glow could be the collective light from a universe-spanning sea of undiscovered dwarf galaxies. These wouldn't be grand spirals like our Milky Way or immense ellipticals. They would be ultra-faint dwarf galaxies, tiny and fragile collections of stars with very little mass. Because they are so small and contain so few luminous stars, their individual light is incredibly feeble, making them nearly impossible to spot at vast cosmic distances. Yet, if they exist in truly staggering numbers far beyond what our current models of galaxy formation predict, their combined, collective output could theoretically account for the strange, uniform glow we see. It's a beautifully simple idea. The light isn't missing. Its sources are just too small and too dim for us to see one by one. This hypothesis has been put to the test in some of the most ambitious astronomical surveys ever conducted. Projects like the Hubble Frontier Fields have used a remarkable natural tool, giant galaxy clusters, as cosmic magnifying glasses. The immense gravity of these clusters bends and amplifies the light from objects far behind them, an effect called gravitational lensing. By staring through these natural telescopes, Hubble has been able to peer deeper and see fainter than ever before, revealing a population of galaxies that were previously invisible. And indeed, it found them, a multitude of tiny, faint dwarf galaxies at the very edge of detection. This was a monumental discovery, but it also delivered a frustrating result. When astronomers carefully counted up all these newly revealed tiny galaxies and calculated their total light, it still wasn't enough. They found more than they expected, but not nearly the vast horde required to fully explain the intense background glow. The deficit, while smaller, remained significant. This leaves cosmologists with a fascinating and profound dilemma that strikes at the heart of how we believe structures form in the universe. Our leading model, known as lambda cold dark matter, makes specific predictions about the number of small galaxies versus large ones. It suggests a certain halo mass function, a cosmic rulebook for how dark matter clumps together to form the gravitational wells that galaxies then develop within. The models predict there should be many more small halos than large ones, but the number of ultra-faint dwarfs needed to explain the intergalactic light would be orders of magnitude greater than even these predictions allow for. So we are forced to ask a radical question. Are our theories about galaxy formation fundamentally incomplete? Perhaps small galaxies form far more efficiently than we thought, converting their gas into stars with an unexpected prowess. Or maybe the very nature of dark matter is different, allowing for many more tiny clumps to form in the early universe than our computer simulations have ever shown. The implications of this are staggering. If this hypothesis were proven correct, it wouldn't just solve one mystery. It would completely overhaul our understanding of the cosmic hierarchy. We would have to accept that the universe is immeasurably more populous than we ever dreamed, filled with a silent majority of tiny, dim galaxies that have been hiding in plain sight all along. This unseen architecture would form the true backbone of the cosmic web, a fine, intricate lacework of light that weaves through the voids between the grand galactic cities. Finding this hidden population is now a primary driving goal for the next generation of observatories, like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope, which are designed to see these faintest of cosmic embers. Their mission is to conduct a definitive cosmic census, to finally count the countless and see if the universe's smallest lights can truly account for its most pervasive glow. But what about the cosmic loners, the stars and planets cast adrift from their galactic homes to wander the eternal darkness alone? The idea of rogue objects flooding the void is a compelling one, painting a picture of a universe filled with untethered nomads. Galactic collisions are violent, chaotic events, and when two galaxies gravitationally tear at each other, the gravitational forces can be so immense that they fling individual stars and even their planetary systems out into the intergalactic medium at incredible speeds. These ejected objects would then travel on endless trajectories through the profound emptiness, their suns burning in isolation, their frozen planets orbiting a star with no galactic address. It's a hauntingly beautiful and lonely existence. Scientists have actually observed this phenomenon on a smaller scale. The Hubble Space Telescope has detected a faint, specific glow coming from within the giant galaxy cluster Able 1689, a glow attributed to the collective light of countless such intergalactic stars. We know these stellar orphans are real. The logical next step is to ask if there could be enough of them, scattered throughout the entire cosmic web, to collectively produce the mysterious uniform background we're trying to explain. The numbers, however, quickly present a serious problem, even with the most generous estimates suggesting there could be billions or even trillions of these rogue objects. The total amount of light they would produce simply doesn't add up to the significant excess we observe. It's like trying to fill an Olympic-sized swimming pool with a garden hose. You'll add some water, but you'll never come close to filling it. An even more significant challenge for this theory is the issue of distribution. Think about how these stars are ejected. They are flung out from their parent galaxies during close encounters or mergers. This means they aren't launched randomly into the cosmos. They are thrown out from the dense regions where galaxies live. Consequently, you would expect these rogue stars to primarily populate the areas relatively close to galaxies and the dense filaments of the cosmic web. They should be rare in the truly deep, empty voids. This would create a background glow that is decidedly not uniform. It would be brighter around galaxy clusters and fainter in the voids, mirroring the clumpy, large-scale structure of the universe itself. Yet, the mysterious light we see is perfectly smooth and even, showing no correlation with the locations of galaxies at all. This creates a fundamental tension that is very difficult for the rogue star hypothesis to overcome. This dead end has led some researchers to consider even more exotic possibilities within this same category. If ordinary rogue stars can't do it, what about something darker? Some have speculated about the potential role of primordial black holes. These are hypothetical black holes that could have formed from the extreme densities in the very early universe, long before the first stars were born. If they exist in vast numbers, and if they are actively consuming sparse intergalactic gas, the infalling material could heat up and emit light before crossing the event horizon. However, this remains highly speculative, with no direct evidence for the existence of such a population. Other exotic objects like quark stars or other strange stellar remnants have also been proposed, but they all run into similar issues of requiring unimaginably large numbers and a mechanism to distribute them so evenly. Ultimately, this particular mystery serves as a powerful lesson in the challenges of cosmic detective work. It highlights the incredible diversity of potential sources we must consider, from the familiar to the fantastical. More importantly, it underscores the immense difficulty of tracking down these faint, isolated emitters in the vastness of space. Finding a single rogue star in the intergalactic void is like searching for a single specific grain of sand on all the beaches of Earth. It pushes our observational capabilities to their absolute limit and reminds us that the darkness between galaxies may hold populations of objects that are, for now, forever beyond our sight, yet whose collective whisper we are just beginning to hear. But what if the answer to this cosmic puzzle isn't hiding in the vastness of space at all, but in the bizarre and counterintuitive realm of the incredibly small? To truly unravel the mystery of the intergalactic glow, we might need to venture beyond the telescope and into the world of quantum mechanics and particle physics. This is where our search takes a thrilling turn, bridging the gap between the largest structures in the universe and the fundamental building blocks of reality itself. Imagine that the faint light filling the voids isn't coming from stars or galaxies, but is instead generated by the very fabric of space-time. One of the most mind-bending proposals involves the quantum vacuum itself. In quantum field theory, a vacuum is not truly empty. It's a seething, bubbling sea of virtual particles that constantly pop in and out of existence. These are called vacuum fluctuations, and while they're fleeting, some theories suggest they could, under certain conditions, produce very real photons, particles of light. If this process is happening everywhere all the time, it could contribute a faint, universal background glow, a literal light from nothingness that permeates every corner of the cosmos. An even more promising candidate from the particle physics world is a hypothetical entity known as an action-like particle. Actions were originally proposed to solve a complex problem in quantum chromodynamics, the theory describing the strong nuclear force, but they quickly became a prime candidate for dark matter. These particles are theorized to be incredibly light and feebly interacting, which would allow them to flood the universe without being directly detected. The fascinating connection to our mystery light comes from a proposed behavior of these particles. In the presence of strong magnetic fields, which undoubtedly exist throughout the intergalactic medium, actions could theoretically undergo a miraculous transformation. Through a process known as the Primakov effect, an action could convert directly into a photon. If vast clouds of action like dark matter are drifting through the cosmic voids, their constant, steady conversion into photons could be the source of the very diffuse glow we're trying to explain. This would mean the light isn't a signal of missing objects, but the shimmering signature of the universe's most elusive substance, finally making itself known through a faint, ethereal radiance. This incredible convergence of cosmology and particle physics represents one of the most exciting frontiers in modern science. The enigmatic glow between galaxies has become a rare meeting point for two fields that traditionally operate on vastly different scales. Particle physicists build massive underground detectors and colossal colliders like the Large Hadron Collider at CERN to smash particles together and probe the fundamental laws of nature. Cosmologists, on the other hand, use immense telescopes to survey the heavens and deduce the history of the universe. The intergalactic background light offers a potential thread connecting these two worlds. A detection of a specific particle, like an action in a lab experiment, could suddenly provide the missing key to explain the astronomical observation. Conversely, precisely mapping the spectrum and distribution of this cosmic glow could tell particle physicists exactly what kind of signatures to look for in their data, guiding their search for new physics. Of course, these ideas remain firmly in the realm of theory for now. The properties required for actions or other exotic particles to produce the observed intensity of light are highly specific and don't always align neatly with other constraints from cosmology and particle physics. It demands a delicate balancing act, often requiring extensions to the standard model of particle physics. Yet, the mere possibility is what fuels scientific discovery. This mystery has effectively turned the entire cosmos into a laboratory. The immense voids between galaxies are no longer empty. They are a testing ground for theories of quantum gravity, dark matter, and forces beyond our current understanding. The faint, pervasive light is a challenge, an invitation to look deeper into the quantum world for answers to a cosmic-scale question, proving that sometimes the keys to the universe's biggest secrets are hidden in its smallest details. This persistent, unexplained glow doesn't just hint at what's out there in space. It might also be telling us a profound secret about when it all happened. The light we see today has been traveling for billions of years, which means it's a direct messenger from the deep past. If this signal is indeed the collective fossilized radiance from the universe's first generations of stars and galaxies, its intensity suggests a dramatic rewrite of our cosmic history book. Our current timeline, carefully constructed from observations of the cosmic microwave background and the large-scale structure of galaxies, paints a picture of a relatively gradual awakening. After the Big Bang, the universe is thought to have spent hundreds of millions of years in a dark, quiet period, slowly letting gravity pull together the first clumps of matter until conditions were finally right for the first stars to ignite. This event, known as cosmic dawn, is a cornerstone of modern cosmology, but the sheer amount of light in this intergalactic background forces us to consider a far more explosive and accelerated beginning. Imagine two possible stories for the early universe. In the first, the story we've long believed, star formation is a slow, steady process, like embers gradually catching and spreading across a vast bed of coals. In the second, the story the glow seems to suggest, the universe bursts into flame almost immediately, with star formation happening at a breakneck pace, like a fireworks finale where everything ignites at once. If the glow is from ancient sources, it implies that the first stars didn't just twinkle on. They blazed into existence much sooner after the Big Bang than our models allow, dramatically compressing the timeline of cosmic dawn. This isn't a minor adjustment. It would mean that the universe got its act together and started building complex structures far faster than anyone thought possible. An alternative, equally radical explanation is that the timeline itself is correct, but the very nature of those first objects was fundamentally different. Perhaps the first stars weren't just larger and brighter, but they formed with an unprecedented efficiency. In the pristine environment of the early universe, composed only of hydrogen and helium with no heavier elements to help gas clouds cool and collapse, our models suggest star formation should have been a challenging process. But what if we're wrong? What if the lack of dust and metals actually allowed for the formation of monstrously large and incredibly luminous stars in even greater numbers than we've simulated? This would mean that the early universe wasn't just making stars earlier. It was making better, more effective light-producing factories, operating at a level of productivity that we see nowhere in the modern cosmos. The initial conditions of the universe may have been far more conducive to creating brilliance than we ever imagined. This puts our most successful cosmological model, lambda cold dark matter, under significant strain. This model beautifully explains the distribution of galaxies we see today and the patterns in the cosmic microwave background. but it predicts a specific, more sedate pace for the early formation of structures. A universe that lights up too quickly creates a serious tension. It could imply that dark matter behaves differently than we think, clumping together faster to form the gravitational seeds for galaxies sooner. Or it might suggest that the physics of gas collapse and star formation in those primordial conditions is governed by rules we haven't yet discovered. The faint glow is therefore a stopwatch, and it's telling us that our clock for the universe's childhood might be running frustratingly slow. Resolving this mystery is one of the primary driving goals for the most powerful telescopes ever built. To peer back to this elusive era, we need to push our technology to its absolute limits, looking for the most distant, redshifted galaxies whose light has been stretched into the infrared by the expansion of the universe. The James Webb Space Telescope, with its unparalleled infrared sensitivity, is designed to do exactly this, to hunt for these pioneer galaxies and directly witness the epoch of first light. By finding and studying these ancient objects, we can finally calibrate our cosmic clock. Do we see galaxies shining when the universe was only 200 million years old instead of 400 million? The answer will either confirm that the timeline needs a major rewrite or send us searching for another, even more exotic explanation for the light that fills the void. This isn't just about fixing a date in a textbook, it's about understanding the very tempo of creation itself. Now we turn our attention to the canvas upon which the cosmic web is painted, the intergalactic medium, or IGM. This is the near-perfect vacuum that exists in the vast expanses between galaxies, a space so empty it makes the best vacuums we can create on Earth seem crowded by comparison. But this void is not entirely empty. It's sparsely populated by an incredibly thin soup of mostly hydrogen and helium gas, along with a whisper of other elements and a pervasive sea of dark matter. It's the fundamental backdrop of the universe, and if our mysterious glow is truly everywhere, then this tenuous medium is the most likely stage upon which it's being produced. One of the most straightforward ideas is that this diffuse gas itself could be the source of the light. If the IGM were heated to tremendously high temperatures, tens of thousands of degrees or more, the gas atoms would become ionized with their electrons stripped away. When those free electrons eventually recombine with protons or get deflected by other particles in a process called Bremsstrahlung radiation, they can emit photons of light. The energy to heat this gas could come from powerful shock waves generated by galaxy collisions or from the intense ultraviolet radiation blasting out from quasars and the first stars. This is a known physical process, and we do see evidence of warm hot gas in the spaces between galaxies within massive clusters. The problem, as always, comes down to the numbers. When cosmologists run the calculations, the amount of light predicted from this known warm-hot intergalactic medium is a tiny, tiny fraction of the intense, pervasive glow we actually observe. It's like trying to heat an entire ocean with a single match. The physics is sound, but the scale is woefully inadequate. This has led scientists to propose that the IGM might be hiding a much more substantial and energetic component than we've accounted for. Perhaps there are vast reservoirs of what's known as the missing baryons, the ordinary matter that our inventories of stars and galaxies tell us should exist, but that we haven't been able to locate. Theorists suggest this matter could be in the form of a filamentary web of extremely hot, low-density gas, 1,000,000 degrees Kelvin or hotter, threading through the entire cosmic web. This gas would be so diffuse and so hot that it wouldn't emit light in a way we can easily detect, but its sheer volume could make it a significant player. Alternatively, the IGM might be densely populated with an immense number of low-mass dark matter halos, invisible structures that never manage to attract enough gas to form stars, but whose gravitational influence or particle interactions could somehow generate or influence light. These ideas push the IGM from a passive backdrop to an active, complex ecosystem brimming with unseen energy. Our primary window into the properties of this elusive medium comes from a clever astronomical technique using the brightest beacons in the universe, quasars. These are the intensely luminous cores of distant galaxies, powered by supermassive black holes greedily consuming material. As the brilliant light from a quasar travels across billions of light years to reach us, it passes through countless filaments of the intergalactic medium. Atoms within that gas, primarily hydrogen, absorb very specific wavelengths of that light, creating a unique fingerprint of dark lines in the quasar's spectrum known as the Lyman alpha forest. By meticulously analyzing this forest of absorption lines, astronomers can deduce the density, temperature, and ionization state of the gas the light passed through. It's a powerful tool, but it has its limits. These absorption studies tell us a great deal about the cooler, denser clumps of gas in the cosmic web, but they are far less sensitive to the proposed widespread sea of extremely hot, diffuse material that could be the true source of the glow. The connection between the detailed maps of the Lyman alpha forest and the uniform, all-sky background light remains frustratingly indirect. This investigation forces a profound shift in perspective. For centuries, astronomy has focused on the brightest objects, the stars, the galaxies, the dazzling beacons that are easiest to see. The mystery of the intergalactic background light compels us to look at the spaces in between. It argues that to truly understand the universe, we must study its entire ecosystem, not just its most luminous inhabitants. The faint, pervasive glow suggests that the empty spaces are not empty at all. They are dynamic and energetically active, filled with processes we are only beginning to imagine. Unlocking this secret will require not just bigger telescopes, but entirely new ways of observing, perhaps by directly detecting the faint emission from million-degree gas or by finding new, subtle signatures in the light from distant quasars. The answers, it seems, are hidden not in the stars themselves, but in the profound and whispering voids that separate them. Now, consider the invisible force fields that weave through the very fabric of the cosmos, a hidden architecture that might hold another piece of this puzzle. Across the universe, from the hearts of galaxies to the deepest voids, space is threaded with magnetic fields. These are not the simple fields of a bar magnet. They are vast, dynamic structures generated by the motion of charged particles in plasma and amplified over billions of years. We know they are there because we can see their influence. They shape the paths of cosmic rays, they sculpt magnificent nebulae, and they can even twist the very light that passes through them. Given their pervasive presence, it's only natural to wonder if these cosmic magnets could be responsible for, or at least contributing to, the mysterious intergalactic glow we're trying to explain. The most well-understood ways magnetic fields interact with light, however, don't seem to fit the bill. Take synchrotron radiation, for example. This is the process where electrons, spiraling at nearly the speed of light around magnetic field lines, emit light. It's a spectacular phenomenon that creates some of the most beautiful and intense radio waves and X-rays we see coming from pulsars and the jets of active galaxies. But the light from synchrotron radiation is very specific. It's polarized and has a characteristic signature that peaks in the radio part of the spectrum, not the broad, unpolarized optical and near-infrared glow that constitutes our mystery signal. Another effect, called Faraday rotation, occurs when a magnetic field twists the polarization plane of light traveling through it. This is an incredible tool for astronomers to measure magnetic field strengths, but it doesn't create new light, it only modifies existing light. So the standard textbook mechanisms fall short, telling us that if magnetism is involved, it's through a far more exotic and unknown process. This is where the theories venture into truly fascinating and speculative territory. Some physicists propose that magnetic fields could act as a catalyst or a converter, transforming one form of energy into the light we see. One compelling idea brings us back to dark matter. If dark matter is made of certain types of theoretical particles like actions, their conversion into photons could be dramatically enhanced in the presence of strong magnetic fields. In this scenario, the intergalactic magnetic fields that permeate the voids would act like a giant, universe-sized catalyst, providing the necessary environment for dark matter to literally shine, producing a faint, uniform glow across the entire sky. It's an elegant concept that would neatly tie together two profound mysteries: the nature of dark matter and the origin of this light using the framework of cosmic magnetism. The monumental challenge, and the reason this remains a speculative frontier, is that we have almost no idea how strong or how structured these intergalactic magnetic fields truly are. Mapping magnetism within a galaxy is difficult enough. Mapping it in the near-perfect vacuum between galaxies is a Herculean task at the very limit of our observational capabilities. The fields are unimaginably weak, billions of times weaker than a common fridge magnet, and their signals are drowned out by brighter sources. We infer their existence indirectly, but their strength, their configuration, and even their origin in the vast cosmic voids are among the biggest open questions in astrophysics. This means that the potential influence of these fields on the intergalactic glow is a complete wild card, a poorly constrained factor that could be negligible or could be the central key to the entire mystery. This immense uncertainty is precisely what makes the magnetic field hypothesis so exciting to a growing number of researchers. It represents a vast and unexplored parameter space in our models of the universe. If future observations were to reveal that intergalactic magnetic fields are stronger or more dynamic than currently believed, it could open up entirely new chapters in physics. It would force us to develop new theories of magnetohydrodynamics, the study of how magnetic fields and plasma interact on cosmological scales, a field ripe for discovery. The quest to understand the faint glow between the galaxies is therefore driving innovation, pushing us to develop more sensitive techniques to probe these faint forces. It's a reminder that the universe is not just made of matter and energy, but also of invisible forces whose subtle influences we are only just beginning to perceive. What if the very framework we use to understand the universe is the thing that's actually wrong? For decades, the lambda-cold dark matter model, or lambdactum, has been the reigning champion of cosmology. It's the standard model, the one that brilliantly explains the large-scale structure of the cosmos, the patterns in the cosmic microwave background, and the accelerating expansion of the universe driven by dark energy. It's been incredibly successful, the bedrock upon which modern astrophysics is built, but the persistent, unexplained intergalactic glow is like a persistent crack in that foundation, a signal that this magnificent theoretical edifice might be missing a crucial piece or even built on slightly flawed assumptions. When a mystery refuses to be solved within the confines of an established model, it's time to start asking if the model itself is the problem, opening the door to some of the most radical and thrilling ideas in all of science. One of the most prominent challenges to the lambdactum model isn't about adding new particles, but about rewriting the rules of the most fundamental force in the cosmos, gravity itself. Our understanding of gravity is entirely based on Einstein's theory of general relativity, which has passed every test thrown at it for over a century. But what if gravity behaves differently on the immense scales of galaxy clusters and the cosmic web? This is the premise of modified Newtonian dynamics, or MN. Instead of invoking huge amounts of invisible dark matter to explain why galaxies rotate faster than they should, MN proposes that gravity simply operates with a different set of rules at extremely low accelerations. While MN was originally designed to explain galaxy rotations, some of its extensions and more sophisticated cousins, like tensor vector scalar gravity, make predictions about the large-scale structure of the universe. If these theories are correct, they would predict a different distribution of matter and energy, which could in turn lead to a different expected background light signal. The unexplained glow could be a direct consequence of gravity working in a way we haven't yet fully grasped, making the fabric of space-time itself the source of the mystery. Venturing even further from the mainstream, some theorists look beyond the three dimensions of space and one of time that we experience daily. String theory and other attempts to unify gravity with quantum mechanics often require the existence of extra, compactified dimensions, tiny, curled-up spatial dimensions that are all around us but are too small to perceive directly. While these ideas are often criticized for being nearly impossible to test, the intergalactic glow might offer a rare opportunity. If these extra dimensions exist, they could allow for interactions or energy transfers that are impossible in a standard four-dimensional universe. For instance, some models suggest that light, or photons, could be produced when particles interact within or leak into these higher dimensional spaces. This would create a diffuse, omnipresent background of light that is a natural byproduct of the universe's true, multidimensional geometry. It's a wildly speculative idea, but it demonstrates how a cosmic anomaly can inspire physicists to explore the very edges of mathematical possibility. Another fascinating, though fringe, set of alternatives involves the constants of nature not being so constant after all. What if the speed of light, or the fine structure constant that governs the strength of electromagnetic interactions, was slightly different in the early universe or in the vast voids between galaxies? Some varying constant theories propose that these fundamental numbers slowly change over cosmic time or space. If that were true, it would completely alter our interpretation of the light we see from the distant past. The properties of how light is emitted and absorbed would be different, potentially leading to a miscalculation of the total background light we expect to see. The excess glow might not be an excess at all, but rather a sign that we've been using the wrong rulebook to interpret the cosmic signals reaching us from across the eons. It would mean the laws of physics themselves are not fixed and universal, but are more like local ordinances that can change from one neighborhood of the cosmos to another. Of course, the vast majority of these alternative models remain on the fringe for a very good reason. They lack the overwhelming predictive power of the standard lambda model. For every problem they might solve, they often create several new ones. However, their value isn't necessarily in being right, but in acting as a vital counterweight that keeps cosmology honest. They force the mainstream to rigorously test its assumptions and prove its superiority. The way to discriminate between these wildly competing theories is through exquisitely precise data. The key lies in measuring not just the intensity, but the full spectrum and the minute spatial variations in the intergalactic glow. Does the light have a specific color signature that matches the predicted decay of a certain dark matter particle? Does its distribution show incredibly faint patterns that align with the filamentary structure predicted by modified gravity? Each theory leaves a unique fingerprint in the light, and our next generation of telescopes will be the cosmic detectives tasked with finding it. This entire endeavor is a powerful reminder that cosmology is not a finished science. It is a field still in its vibrant, tumultuous adolescence. The existence of a profound mystery like the intergalactic background light is not a sign of failure. It is the engine of scientific revolution. It was the orbit of Mercury that didn't quite fit Newton's laws, a tiny anomaly that helped pave the way for Einstein's relativity. It was the unexpected recession of galaxies that revealed the expanding universe. Today, this faint glow is that same kind of anomaly, a persistent data point that refuses to fit neatly into our current understanding, whispering that a paradigm shift might be waiting just over the horizon, ready to reveal a cosmos far stranger and more wonderful than we ever imagined. Every time we push the boundaries of our vision, the universe reveals deeper layers of its complexity, and our current generation of telescopes, as magnificent as they are, have brought us to the very edge of their capabilities in this search. Hubble and New Horizons have served as our primary detectives in this case, uncovering the mystery of the intergalactic glow, but they lack the specific tools to identify the culprit. It's like having a camera that can tell you a room is faintly lit, but its lens isn't sharp enough to distinguish whether the light is coming from a multitude of tiny nightlights, a single dim lamp, or perhaps something even more unusual like gently glowing walls. The light we've detected is a tantalizing clue, but to move from a clue to a solution, we need a new class of investigative tools designed specifically for this deep cosmic forensics. This is where the next generation of space observatories enters the story, instruments that represent a quantum leap in our ability to dissect this faint signal. The James Webb Space Telescope, with its colossal gold-plated mirrors and suite of incredibly sensitive infrared instruments, is uniquely equipped to hunt for one of the prime suspects, the very first galaxies. Webb's infrared vision is perfect for detecting the highly redshifted light from these ancient objects, allowing it to peer back further in time than any telescope before it. If a population of undiscovered, ultra-faint primordial galaxies is responsible for the glow, Webb is our best bet for finally spotting them. Meanwhile, the upcoming Nancy Grace Roman Space Telescope will take a different, equally vital approach. Roman is designed to conduct massive, wide-field surveys of the sky, capturing enormous swaths of the cosmos in incredible detail. Its mission is to conduct a definitive cosmic census, counting and measuring the faintest dwarf galaxies and intra-cluster stars with unprecedented statistical power. If the answer lies in a vast number of relatively nearby but incredibly dim objects that Hubble could only see in tiny, targeted patches, Roman will find them. Yet there's a profound and humbling possibility that even these technological marvels might not provide a definitive answer. What if the light isn't coming from discrete points at all? If the glow is truly diffuse, produced by a process like the decay of dark matter particles or the emission of a warm intergalactic gas, then no telescope, no matter how powerful, will ever resolve it into individual sources. It would be like trying to use a microscope to see the individual molecules that make water appear blue. The property is inherent to the medium itself, not a collection of tiny blue objects. In this scenario, these incredible observatories will still be invaluable, but their role will shift from identification to elimination. They will rule out entire classes of explanations, telling us with great certainty what the glow is not, thereby narrowing the field for theorists and forcing us to confront even more exotic physics. This beautiful and sometimes frustrating dance between technology and discovery is a fundamental rhythm of scientific progress. We build a new instrument to answer an old question, and in doing so, it reveals a dozen new, even more perplexing mysteries we never thought to ask. The journey to understand this faint intergalactic light is not just about solving one puzzle. It is a powerful engine driving innovation across the entire field of observational astronomy. The need to measure this incredibly subtle signal is pushing engineers to design detectors with even lower noise, to create new methods for suppressing stray starlight, and to develop advanced AI algorithms capable of the meticulous subtraction required to see the signal against the overwhelming cosmic background. The mystery itself is forcing us to become better, more precise observers, and the technological spin-offs from this pursuit will undoubtedly benefit every other branch of astronomy, from the search for exoplanets to the study of distant black holes. The light that shouldn't exist is, in a very real way, illuminating the path toward our future in space. But beyond the equations and the data, this unexplained light pushes us into a realm far older than modern astrophysics, the domain of pure philosophy. For centuries, we have operated under a fundamental assumption that the universe is ultimately knowable. We believe that through careful observation, rigorous experiment, and the application of reason, we can unravel its secrets and write a complete set of rules, a grand theory of everything. This mysterious glow, this light with no source, is a stark and humbling reminder that this assumption might be a beautiful, hopeful fiction. It whispers that there may be entire layers of reality operating just beyond the periphery of our current understanding, realms that our physics, in its present form, is simply not equipped to describe. This isn't a failure of science, it's a revelation of its true frontier, the boundary where established knowledge meets the vast, uncharted territory of the unknown. This confrontation with the limits of our knowledge inevitably spirals into profound existential questions. If our most powerful telescopes and our most brilliant minds cannot account for something as fundamental as light in the void, what else are we missing? The glow could be a subtle signal from a neighboring universe in a vast multiverse, a ghostly leakage from a cosmos with entirely different physical constants. Or perhaps it's evidence that the laws of physics we hold to be universal and constant are actually more like local bylaws, applicable in our galactic neighborhood but subject to variation in the great intergalactic deserts. These are not ideas from science fiction. They are serious, albeit speculative, extensions of cosmological thought that this single anomaly forces us to consider. It challenges our anthropocentric view, the quiet notion that our human-scale perception and intellect are the ultimate yardsticks for measuring reality. Ultimately, this isn't just a puzzle about photons, it's a mirror reflecting our own place in the cosmos. The feeling it evokes is an ancient one, a sense of awe that is equal parts wonder and disquiet. We are a species on a tiny rock, orbiting an average star in a quiet suburb of a galaxy, daring to map the entirety of existence. And just when we think our map is nearly complete, the universe sends a faint, uncanny glow to remind us of how much paper is still left blank. This fosters a necessary humility, a counterbalance to the arrogance that can sometimes accompany scientific triumph. It returns us to a state of childlike curiosity, where the universe is not a problem to be solved but a mystery to be embraced, a constant source of wonder that ensures the journey of discovery never truly ends. What makes the intergalactic glow so fascinating isn't just its own mystery, but the company it keeps. It turns out this unexplained light is far from alone in the cosmic hall of puzzles. It's part of a growing collection of astronomical anomalies that refuse to fit neatly into our established models. Each of these mysteries stands as a monument to our current ignorance, a stubborn data point that the universe seems to be waving at us, insisting we're missing something fundamental. There's dark energy, the mysterious force causing the expansion of the universe to accelerate, which makes up about 68% of the cosmos, yet whose nature remains completely unknown. Then there are fast radio bursts, incredibly intense, millisecond-long blips of radio energy that flash across the cosmos from unknown sources billions of light-years away, some repeating in patterns we can't decipher. And perhaps most pressingly, there's the Hubble tension, a growing crisis in cosmology where two of our most precise methods for measuring the universe's expansion rate yield stubbornly different results, suggesting a fundamental flaw in our understanding of cosmic history. When you step back and look at these puzzles together, a tantalizing possibility emerges. What if these aren't separate, unrelated problems, but different symptoms of the same underlying gap in our physics? Perhaps the same unknown ingredient or process that's causing the universe's expansion to accelerate dark energy is also contributing to the production of this unexplained intergalactic light. Or maybe the exotic objects or violent events that create fast radio bursts are also prolific emitters of the diffuse optical glow we're detecting. The most compelling parallel might be with the Hubble tension. This discrepancy in the expansion rate suggests that our standard model of cosmology, lambda cold dark matter, might be missing a crucial component. If that's true, it's entirely possible that this missing component is also the source of the background light. An early population of unknown particles or a modification to gravity that affects the expansion rate could simultaneously be producing photons, linking these two great mysteries at a fundamental level. This shift in perspective, from studying these anomalies in isolation to examining them as parts of a connected whole, represents a new, integrative approach to cosmology. Instead of having separate teams of specialists working on dark energy, another group on fast radio bursts, and yet another on the intergalactic glow, there's a growing movement to break down these silos. Scientists are now building cross-disciplinary models that attempt to solve two or more of these puzzles with a single, elegant extension of physics. For instance, a new form of dark energy that evolves over time could potentially affect the expansion rate, influence the formation of structures that create radio bursts, and even decay into photons that contribute to the background glow. Similarly, certain types of exotic dark matter could explain the missing mass. Its decay products could produce the light, and its gravitational influence could subtly alter the expansion history of the universe, resolving the Hubble tension. This holistic strategy is more than just efficient. It's becoming essential for true progress. If you try to solve each mystery by inventing a new, separate physical phenomenon for each one, you end up with a cluttered, inelegant model that lacks predictive power. But if you can find a single new principle or particle that addresses multiple anomalies at once, you're far more likely to be on the right track. This is the essence of the scientific method. The most powerful theories are those that explain the most with the least. The simultaneous emergence of these several major puzzles in cosmology is therefore not a cause for despair, but a tremendous opportunity. It's as if the universe has given us not one but several different keys, and the challenge is to find the one lock they all fit. The intergalactic background light, shining faintly in the void, may be the crucial piece that finally allows us to see the pattern connecting all these cosmic mysteries, guiding us toward a deeper, more unified understanding of the reality we inhabit. And in a beautiful twist, the quest to understand this cosmic mystery isn't confined to the hallowed halls of universities or the control rooms of space agencies. It's a search that has thrown its doors wide open, inviting anyone with an internet connection and a curious mind to join the investigation. This is the world of citizen science, a collaborative movement that is fundamentally changing how we explore the universe. Projects like Galaxies Zoo have brilliantly demonstrated that the human brain, with its incredible pattern recognition skills, can sometimes spot subtle anomalies and faint structures that even the most sophisticated computer algorithms might overlook. By presenting volunteers with millions of images of galaxies captured by robotic telescopes, these initiatives harness the collective power of thousands of eyes, turning the global public into a single, massive research team working to classify the cosmos. This isn't just busy work, it's a genuine and vital contribution to astrophysics, where a volunteer sitting at their kitchen table might be the first person to ever lay eyes on a rare and important celestial object. This approach is perfectly suited for a puzzle like the intergalactic background light. The data involved is staggering countless images from deep field surveys where the potential sources of the glow could be hidden as infinitesimally faint smudges or unexpected patterns of pixels. Distributing this Herculean task across a global network of volunteers doesn't just accelerate the research, it democratizes discovery itself. It shatters the old model where a small, elite group of experts holds the sole key to scientific inquiry, replacing it with a wonderfully inclusive spirit that says the wonder of the cosmos belongs to everyone. For the individual participant, it's a chance to feel a genuine connection to the cutting edge of human knowledge, to be part of something infinitely larger than themselves. That moment of personal contribution, of knowing you might have helped pinpoint a distant, unknown galaxy, fosters a deep and lasting engagement with science that no textbook or documentary can ever replicate. Beyond the direct analysis, the very nature of this mystery makes it a powerful tool for public outreach and education. The question it poses, why is there light where there shouldn't be, is instantly graspable. It doesn't require an advanced degree in physics to appreciate its profound weirdness and allure. This accessibility makes it a perfect gateway to inspire future generations of scientists, engineers, and thinkers. By presenting this unsolved puzzle to students and the public, we're not just sharing a fact, we're inviting them into the ongoing process of science itself. We're showing them that the universe is still full of questions waiting for their answers, encouraging them to cultivate the critical thinking and boundless curiosity that will drive the next great leap in our understanding. This collaborative spirit, blending professional expertise with public passion, is becoming an essential strategy for tackling the most profound questions, proving that sometimes the most powerful instrument in discovery isn't a telescope but a connected community. Pursuing a mystery that lies in the deepest voids of space inevitably brings us back to a very earthly question: what is the price of cosmic curiosity? Unraveling the secret of the intergalactic glow is not a cheap endeavor. It demands the construction of ever more sensitive space telescopes, the funding of large research teams for years of painstaking analysis, and the development of groundbreaking technologies just to get a slightly clearer look. This level of investment naturally prompts a vital debate about resource allocation. In a world facing immediate and pressing challenges like climate change, poverty, and disease, can we truly justify spending billions of dollars to study a faint, unexplained light between galaxies? It is a question that deserves a thoughtful answer, and the response lies not in the stars themselves, but in the unexpected and profound ways that the quest for pure knowledge circles back to benefit us all right here on Earth. The history of science is filled with stories of fundamental research that seemed abstract and impractical at the time, only to yield world-changing technologies we now take for granted. The Charge-Coupled Device, or CCD, is a perfect example. This incredibly sensitive light sensor was originally developed in the late 1960s for astronomy, allowing telescopes to capture faint starlight with far greater efficiency than photographic film. Without the driving need to see deeper into the cosmos, its development might have been delayed for decades, Today, the CCD and its descendants are in every smartphone camera, in medical imaging machines that save countless lives through earlier disease detection, and in countless security and industrial systems. This is not an isolated case. The need to process the enormous datasets from astronomical surveys helped drive the development of powerful image analysis algorithms that now power everything from facial recognition software to diagnostic tools in healthcare. The pursuit of one mystery creates a ripple effect of innovation that touches nearly every aspect of modern technology. Beyond these tangible technological spin-offs, there's an even more valuable return on investment, the inspiration of a new generation. A profound cosmic mystery, like a light that shouldn't exist, captures the public imagination in a way that few other things can. It sparks wonder and curiosity in young minds, drawing them into the fields of science, technology, engineering, and mathematics. A child who is captivated by the story of this enigmatic glow might be inspired to become the engineer who designs the next great telescope, the computer scientist who writes the algorithms to decode its data, or the physicist who finally devises the theory that explains it all. This influx of talent and passion into STEM fields is an incalculable long-term benefit to society, fueling economic growth and driving innovation across all industries, not just astronomy. The money invested in solving a cosmic puzzle is, in a very real sense, an investment in our collective intellectual capital and our future problem-solving capacity. Ultimately, the debate touches on the very philosophy of what makes a civilization truly great. Should we only fund research that promises an immediate, direct payoff, or do we also value the pursuit of knowledge for its own sake? Exploring the fundamental nature of the universe is a deeply human endeavor, a signature of a society that looks outward and dreams bigger than its daily needs. The economic implications of solving the intergalactic light mystery are therefore twofold. There are the direct, practical benefits, the new technologies, the skilled jobs, and the educational opportunities it creates. But there is also the intangible value of living in a world that still believes in discovery, that is willing to invest in questions simply because they are profound and beautiful. This commitment to fundamental understanding is what pushes humanity forward, ensuring that our future is not just one of comfort, but one of continued wonder and limitless possibility. As we reach ever further into the cosmos, chasing the source of this enigmatic light, we must also pause to look inward and consider the weight of what we might find. The pursuit of pure knowledge, for all its noble intentions, is never entirely separate from the ethical landscape it will inevitably alter. While the intergalactic glow itself is almost certainly a natural, abiotic phenomenon, the journey to understand it could lead us down paths that challenge the very foundations of our worldview. Every great cosmic discovery has carried this dual edge, the potential to enlighten and the power to destabilize. Consider the Copernican revolution, which didn't just rearrange the solar system. It dethroned Earth from the center of the universe, triggering a profound and painful re-evaluation of humanity's place in the grand scheme of things. The discovery of this light could be a similar pivot point, forcing a reckoning with new truths we are not yet prepared to accept. Imagine for a moment that the ultimate explanation for the glow is something truly paradigm-shattering. Suppose it provides the first solid evidence for a multiverse, a vast, perhaps infinite, ensemble of other universes beyond our own, each with its own unique physical laws. On one hand, this would be the most breathtaking expansion of reality ever conceived, but it also raises deep, disquieting questions about uniqueness and purpose. If our universe is just one of countless others, a single page in an infinite library, does that diminish the specialness of our existence? concepts central to human culture, religion, and philosophy, ideas of a unique creation, a special destiny, or a universe fine-tuned for life, would be challenged in ways we can barely anticipate. This isn't just abstract physics, it's a potential cultural earthquake that could reshape our collective identity, and scientists have a responsibility to consider how such a discovery is communicated and contextualized for a global society. This ethical dimension extends beyond the philosophical and into the practical. The technological drive to solve this mystery, to build bigger telescopes and more powerful sensors, is part of a larger ecosystem of scientific exploration. This progress must be balanced against our responsibility as stewards of our own planet and the orbital environment around it. The launch of ever more satellites and space observatories contributes to the growing challenge of space debris, creating a potential hazard for future generations. There's an ethical imperative to pursue these grand questions sustainably, to ensure that our quest to understand the distant cosmos doesn't come at the cost of creating a shell of inaccessible junk around our own world, trapping us on the very planet we are trying to see beyond. The choices we make today in funding and conducting this research will echo for centuries, for better or worse. Furthermore, the global collaboration required for this endeavor itself presents an ethical opportunity. The mystery of the intergalactic globe belongs to no single nation. It is a puzzle for all of humanity. How we choose to structure that collaboration, whether we foster open data sharing and inclusive international partnerships, or allow it to become a new arena for competition and division, will set a precedent for how we handle future cosmic discoveries. Will the benefits of the knowledge and the technologies spun off from it be shared broadly, or will they exacerbate existing global inequalities? The ethical approach is to use this shared curiosity as a bridge, demonstrating that our common humanity and collective thirst for understanding can transcend terrestrial borders and conflicts. In this way, the search for a faint light in the void becomes a test of our maturity as a species, asking not just what we can discover, but who we choose to be on the journey. And so our investigation takes a fascinating turn, from the vast emptiness between galaxies to the potential for life within them. While the mysterious intergalactic glow isn't a signal from some cosmic civilization, its presence could fundamentally reshape the very environments where life might take root. Think of this pervasive light as a subtle but constant background actor on the cosmic stage, one that influences the conditions for every potential player. Every planet orbiting a star exists within a complex radiation environment, bathed not just in the light of its own sun, but in the collective glow of its entire galaxy, and as we're now learning, this faint, universal light from the void. This background radiation contributes to a planet's overall energy budget, a delicate balance that can influence climate, atmospheric chemistry, and ultimately, the potential for life to emerge and thrive. Consider the concept of the galactic habitable zone. Astronomers often discuss the region within a galaxy where conditions are just right for life, not too close to the violent, radiation-blasted galactic center with its frequent supernova, and not too far out in the metal-poor outskirts where there aren't enough heavy elements to form rocky planets. This mysterious intergalactic glow adds a new, faint layer to that equation. If this light is significantly more intense than we thought, it represents a constant, low-level source of energy washing over every planet. On one hand, for a world orbiting a dim red dwarf star on the cooler edge of its habitable zone, this extra background illumination could provide a subtle warming effect, perhaps nudging a frozen world into a more temperate range. Conversely, for a planet already receiving ample starlight, this additional energy could contribute to atmospheric stripping or increase mutagenic radiation levels at the surface, pushing our otherwise habitable world into a dangerous zone. It's a reminder that habitability isn't just about a single star. It's about a planet's place in the entire cosmic ecosystem, including the light from the great beyond. The implications become even more profound if the source of this light turns out to be something truly exotic, like decaying dark matter. If that's the case, then the potential for life might be intertwined with the distribution and behavior of the universe's most mysterious substance. Imagine a galaxy with a dense, active dark matter halo that produces a more intense local glow, potentially creating radiation barriers that limit where life can safely evolve. Alternatively, this process could provide a steady, gentle source of energy deep within interstellar space, perhaps even within rogue planets flung from their solar systems. These lonely worlds adrift in the darkness were once thought to be utterly frozen and lifeless. But if they are being gently warmed not by a star, but by the faint universal glow of dark matter decay, could their subsurface oceans remain liquid? It's a staggering thought that the seeds of life might not require a sun at all, but could be nurtured by the invisible dark matter that permeates all things, suggesting habitats far more bizarre and widespread than we ever dreamed. This connection forces astrobiologists to broaden their horizons dramatically. The search for life has traditionally focused on finding Earth-like planets around Sun-like stars, worlds where conditions mirror our own. But if new physics is at play, revealed by this unexplained light, then the rulebook for biology might be far more expansive. Life could potentially exploit energy sources and thrive in environments we currently consider far too extreme or energetically poor. The intergalactic glow, therefore, is more than a cosmic curiosity. It is a key that could unlock a new understanding of life's potential resilience and diversity. By solving the mystery of this light, we aren't just answering an astrophysical question. We are potentially redefining the boundaries of the living universe itself, wondering if we are surrounded by a cosmos that is not only stranger than we imagine, but stranger than we can imagine, teeming with possibilities we are only just beginning to glimpse. This fascination with celestial light is etched into the very bedrock of human civilization. Long before the first telescope was pointed at the heavens, our ancestors looked up at the night sky and saw more than just points of light. They saw a canvas for their deepest fears, hopes, and questions. They wove the stars into the fabric of their myths. The Milky Way became a river of souls, a path for gods, or the spilled milk of a divine mother. Constellations told epic stories of hunters, scorpions, and swans, serving as both a celestial storybook and a navigational guide for early explorers. This innate drive to find meaning and narrative in the cosmos is a thread that connects the earliest stargazers to the modern scientists staring at Hubble's deepest fields. The unexplained intergalactic glow is simply the latest chapter in this ancient story, a new celestial mystery for a new age, proving that our sense of wonder is as powerful today as it was thousands of years ago. This new mystery provides a rich, modern mythology, a source of inspiration that fuels creativity across countless disciplines. For filmmakers and science fiction authors, the concept of a pervasive, unexplained light in the void is a narrative goldmine. It evokes the same profound sense of awe and mystery that black holes or alien megastructures once did, offering a scientifically grounded yet deeply enigmatic concept to explore. A novelist might imagine it as the fading echo of a long-dead civilization's final, desperate broadcast, a message forever lost in the vastness. A filmmaker could visualize it as the energy signature of a higher dimensional realm brushing against our own, a visual representation of the universe's hidden layers. This glow gives artists and storytellers permission to dream on a cosmological scale, using real science as a springboard for incredible speculation. It provides a shared cultural touchpoint, a concept that is both intellectually rigorous and endlessly imaginative, allowing the mystery to leap from scientific journals into the broader public consciousness. Perhaps most importantly, this scientific pursuit actively bridges the centuries-old divide between the sciences and the humanities. For too long, these have been viewed as two separate cultures, one dealing with cold, hard facts and the other with emotion and subjective experience. The intergalactic glow effortlessly dismantles this artificial barrier. Here, we have a phenomenon that is rigorously measured and quantified by the world's most advanced instruments, yet its very existence sparks profound philosophical questions about our place in the universe and the nature of reality itself. It forces a dialogue between the astrophysicist calculating photon flux and the philosopher pondering the meaning of the unknown. It invites the historian to draw parallels with past astronomical revolutions, and it challenges the artist to find a way to represent this intangible, ethereal concept in a form we can feel and experience. This single, faint signal demonstrates that the quest for knowledge is not a sterile, isolated endeavor, but a deeply human one that feeds our collective need for story, meaning, and beauty. In this way, the light that shouldn't exist does more than challenge physics. It continues a timeless human conversation. It is a modern campfire story told with the language of mathematics and the evidence of pixels, yet it evokes the same primal curiosity that our ancestors felt under a canopy of stars. It reminds us that science does not kill wonder. It refines it, offering ever deeper and more profound mysteries to captivate our imagination. Each new discovery, rather than closing the book on the unknown, simply adds more pages, ensuring that the cultural and historical significance of looking up at the sky will continue to inspire, terrify, and delight us for generations to come. Now think about the power of this mystery not just for researchers, but for the classroom. The story of the unexplained intergalactic glow is a perfect, real-world catalyst for teaching the very heart of the scientific method. It's a narrative that's still being written, which makes it incredibly compelling for students. Instead of just memorizing facts from a textbook about the electromagnetic spectrum, they can see it in action. They can learn how astronomers use different wavelengths of light, from optical to infrared, as tools to dissect this cosmic puzzle, understanding that each part of the spectrum reveals a different piece of the story. This transforms an abstract concept into a tangible detective kit used by real scientists. Educators can use this ongoing mystery to demonstrate that science is not a static set of answers, but a dynamic process of questioning. A lesson can begin with the initial observation, the Hubble and New Horizons data showing a signal that shouldn't be there. Students can then be guided through the process of hypothesis generation, exploring the various theories we've discussed, from rogue stars and dark matter decay to unknown galaxies. They can critically evaluate each one, discussing the evidence that supports it and the challenges it faces, like the problem of the light's uniformity. This teaches them that science often involves living with uncertainty, weighing competing ideas, and revising your understanding when new data comes in. It's a powerful antidote to the misconception that science is about memorizing unquestionable truths. Furthermore, this topic beautifully bridges multiple scientific disciplines, showing how they interconnect to solve a grand problem. It's not just astronomy, it involves physics to understand particle decay, chemistry to consider the composition of dust, and even geology by analogy, comparing the cosmic background light to a fossil record that we must learn to interpret. This interdisciplinary approach helps students see the bigger picture and understand that major discoveries often happen at the boundaries between fields. It encourages a holistic way of thinking, showing that knowledge isn't created in isolated silos. Perhaps most importantly, this mystery serves as a profound tool for fostering critical thinking and intellectual humility. It demonstrates the limits of our current knowledge in a way that is exciting rather than discouraging. It shows students that there are still massive, fundamental questions waiting for answers, and that those answers might one day come from them. By incorporating this cutting-edge enigma into curricula, we do more than just teach facts, we inspire a mindset. We encourage students to embrace curiosity, to tolerate ambiguity, and to develop the analytical skills needed to navigate a complex world. This isn't just about creating the next generation of astronomers. It's about empowering all students to become more thoughtful, questioning, and engaged citizens, equipped to tackle the great unknowns of their own time, whatever they may be. It's a humbling thought, but some of the most profound discoveries in human history weren't the result of meticulous planning, they were happy accidents. The story of science is filled with these beautiful moments of serendipity, where a researcher looking for one thing stumbled upon something entirely different and far more important. Alexander Fleming famously returned from vacation to find a mold called Penicillium notatum contaminating his Petri dishes, but instead of discarding them, he noticed the bacteria around the mold had been killed. That simple, observant moment gave the world penicillin. Arno Penzias and Robert Wilson at Bell Labs were trying to eliminate a persistent, annoying static hiss from their giant radio antenna, a noise they blamed on pigeon droppings. After cleaning the antenna thoroughly, the noise remained, leading them to the monumental, unintended discovery of the cosmic microwave background radiation, the afterglow of the Big Bang itself. These weren't failures, they were breakthroughs in disguise, waiting for someone with the wisdom to recognize an unexpected gift. This grand tradition of accidental discovery is deeply woven into the very fabric of astronomy and continues to this day with the mystery of the intergalactic glow. When astronomers first pointed the Hubble Space Telescope at those deep, dark voids, their primary goal wasn't to find an unexplained light. They were hunting for something else entirely, perhaps the faintest, most distant galaxies or clues to the structure of the cosmic web. They were executing a carefully designed observation plan, a targeted mission with specific objectives. The glow itself was an uninvited guest in their data, a background signal that was supposed to be subtracted away as noise. It was the anomaly that refused to disappear, the persistent whisper that wouldn't be silenced. They weren't looking for it, but because they were open-minded and incredibly thorough, they didn't ignore it. They followed the clue, and it led them to one of the biggest cosmological puzzles of our time. This highlights a crucial tension in modern science between targeted research and curiosity-driven exploration. In an era of tight funding and highly specific grant proposals, there's immense pressure to deliver precise results on a predetermined timeline. Research is often expected to be a straight line from a hypothesis to a conclusion. But the history of discovery tells us that the path to true innovation is rarely so direct. It's often messy, winding, and full of unexpected detours. The greatest revelations frequently come from the side quest, the unexplained blip on the graph, the data point that makes no sense at first glance. This intergalactic glow is a powerful testament to the value of leaving room for that messiness, for allowing scientists the freedom to pursue an oddity simply because it's odd. It argues for protecting a space for pure, unstructured curiosity within the scientific enterprise. What does it mean to truly embrace serendipity in science? It's more than just getting lucky, it's a cultivated mindset. It requires creating an environment where researchers have the freedom to explore tangents without fear of failure. It means building instruments and missions that are flexible, that can be used in novel ways to investigate surprises as they arise. Most importantly, it demands a deep respect for observation over expectation. The courage to let the universe tell us what's important, rather than forcing it to conform to our preconceived models. The astronomers who discovered the cosmic optical background could have easily dismissed it as an instrumental error or a data processing artifact. Instead, they chose to lean into the mystery, to devote years of their careers to verifying and understanding this signal they never intended to find. As we look to the future and the next generation of telescopes, the lesson of this mysterious glow is clear. While we must certainly build these incredible machines with specific, ambitious goals in mind, we must also design them to be discoverers of the unknown. We must hope that they find things we didn't anticipate, anomalies that force us to rewrite our textbooks. The key to solving this cosmic puzzle, and countless others waiting in the darkness, may not lie in a more focused research proposal, but in a willingness to wonder, to be surprised, and to appreciate the incredible discoveries that happen not when we find the answers we're looking for, but when we stumble upon the questions we never thought to ask. This profound cosmic puzzle is far too vast for any single nation or institution to solve alone. It demands a truly global response, a united front of human curiosity and ingenuity. Astronomers from every corner of the world are now pooling their resources, sharing precious time on the most powerful telescopes ever built. Teams in Chile are pointing the immense mirrors of the Very Large Telescope, or VLT, at the darkest patches of sky, while their colleagues in Japan are doing the same with the Subaru telescope in Hawaii, gathering data from a different hemisphere and a different perspective. This isn't a competition, it's a coordinated, worldwide campaign to corner a mystery that belongs to all of humanity. Soon, this effort will be supercharged by the next generation of observatories, like the mind-bogglingly large, extremely large telescope currently rising from the Atacama Desert. Its 39-meter wide primary mirror will collect more light than any optical instrument in history, offering an unprecedented view into the faint glow. But even this colossal eye on the sky will only see part of the picture. Its data will be immediately shared and cross-referenced with findings from the James Webb Space Telescope and other international facilities, creating a composite, global view that is infinitely greater than the sum of its parts. What's truly beautiful about this collaboration is how it transcends the traditional boundaries that often divide us. In the pursuit of this enigmatic light, nationality, politics, and cultural differences fade into the background. A researcher in India, a data analyst in Germany, and a theorist in Brazil are all united by a common, profound question that has nothing to do with borders and everything to do with our shared existence in the universe. This shared goal fosters a unique form of diplomacy, built not on negotiation, but on a mutual passion for understanding. Conferences and video calls become melting pots of perspectives, where different ways of thinking and problem-solving collide to create innovative new approaches. The mystery of the intergalactic glow, in its sheer universality, becomes a powerful reminder that we are all citizens of the same pale blue dot, looking up at the same cosmic mystery. It exemplifies how science can serve as one of the most powerful unifying forces on the planet, building bridges of cooperation and respect through the simple, shared language of curiosity. This global endeavor also champions a crucial, modern scientific ideal, the principle of open data. The teams involved understand that to crack this case, they cannot work in isolated silos, guarding their findings. Instead, they are committed to making their observations and analyses publicly available to the entire research community as quickly as possible. This open data policy does more than just accelerate progress, it democratizes discovery. It allows a brilliant graduate student at a university with a small budget to access the same world-class data as a senior professor at a major institute, ensuring that the next groundbreaking idea can come from anywhere. It invites fresh eyes and diverse perspectives, which are absolutely essential for a problem this stubborn. A physicist might see a pattern in the data that an astronomer overlooks, or a computer scientist might develop a novel algorithm to subtract background light in a way no one had considered. By building an inclusive, global research community, we are not just increasing the number of people working on the problem, we are expanding the very nature of how we think about it, bringing every available tool in the human intellectual arsenal to bear on the darkness. This collective effort stands as a powerful testament to what we can achieve when we choose to look up together, embracing our shared wonder about the cosmos we all call home. This relentless pursuit of a faint whisper of light in the cosmic darkness is far more than an intellectual exercise. It is a powerful engine for technological revolution. To even detect this elusive intergalactic glow, we had to first invent entirely new classes of instruments with almost unimaginable sensitivity. The charge-coupled devices, or CCDs, in telescopes like Hubble were already marvels of engineering, but the need to peer even deeper into the void is pushing us to create their successors. We are now developing ultra-low noise sensors that are cooled to within a fraction of a degree of absolute zero to minimize their own thermal emissions, allowing them to register the faintest possible photons from the edge of oblivion. The quest doesn't stop at the detector, it extends to the entire optical system. To eliminate the merest hint of stray light from within the telescope itself or from bright objects just outside its field of view, engineers are designing increasingly complex and effective baffling systems. These are like cosmic sunshades built into the telescope tube, using a series of specially designed ridges and blackened surfaces to trap unwanted light, ensuring that only the pristine darkness of the deep void reaches the sensor. This isn't just about building a better camera, it's about redefining the very limits of observation, creating eyes that can see the almost nothing, yet capturing the raw data is only half the battle. The other half is a monumental challenge in computational astrophysics, a field being utterly transformed by this mystery. Think of the data from an ultra-deep field observation as an immensely complex, multi-layered image where the signal you want is buried beneath a mountain of noise and foreground light. Isolating the intergalactic glow requires a process of digital subtraction so precise it borders on art. Astronomers must create exquisitely detailed models of every known source of contamination. The faint glow of zodiacal light from our own solar system's dust, the integrated light from all the galaxies too dim to be resolved individually, even the subtle airglow from Earth's upper atmosphere for ground-based telescopes. Subtracting these layers is like trying to hear a single, quiet instrument in a massive orchestra by perfectly silencing every other musician, one by one. This is where machine learning and artificial intelligence are becoming indispensable partners. Scientists are training sophisticated neural networks on vast simulated datasets, teaching them to recognize the unique statistical signature of the background glow and to separate it from the cosmic clutter with a precision far beyond traditional methods. These algorithms are learning to see the invisible, and in doing so, they are pushing the entire field of data science into new territory. The most beautiful aspect of this technological spin-off is that it rarely stays confined to the realm of astronomy. The innovations driven by our cosmic curiosity have a powerful habit of rippling out into the wider world, solving earthly problems in unexpected ways. Those incredibly sensitive CCD sensors developed for deep space observation are the direct ancestors of the imaging chips in modern medical equipment. The same technology that gathers photons from across the universe is now used in digital mammography and dental X-ray systems, detecting tumors and cavities with stunning clarity to save and improve lives. The advanced machine learning algorithms honed to subtract galactic light are now being adapted to analyze medical scans, where they can identify subtle patterns indicative of disease long before the human eye might see them, leading to earlier diagnoses and better outcomes. Even the complex image processing techniques developed to clean up cosmic data find applications in remote sensing for climate science, helping us monitor deforestation, track polar ice melt, and manage agricultural resources with greater accuracy. The drive to understand a faint glow between galaxies ultimately helps us see our own world more clearly. This creates a powerful and symbiotic cycle of innovation. Fundamental, curiosity-driven research asks the big, seemingly impractical questions that demand new technological solutions. In striving to build those solutions, engineers and scientists create groundbreaking new tools and techniques. Those tools, in turn, find immediate and vital applications that benefit society, drive economic growth, and improve our quality of life. The money and brainpower invested in solving a cosmic mystery, therefore, yield a double dividend. They advance our understanding of the universe while simultaneously seeding the technological landscape with the next generation of practical inventions. The quest to understand the light that shouldn't exist is a perfect example of this virtuous cycle, proving that the journey to answer our deepest questions about the cosmos is also, inevitably, a journey that shapes a better future for humanity right here on Earth. There's a deep and fundamental part of the human psyche that is both terrified and mesmerized by what we don't understand. We are hardwired for curiosity, yet we also possess an instinctive caution for the unfamiliar. This internal dance between fear and fascination is at the very core of our being, and the mystery of the intergalactic glow taps directly into this primal nerve. It's not just a data point on a graph. It's a psychological phenomenon, a story that the universe is whispering to us, and something in our soul is compelled to lean in and listen. This cosmic puzzle does more than challenge our equations. It speaks to a profound human need for wonder, for that feeling of awe that momentarily lifts us out of our daily routines and reminds us that we are part of something impossibly vast and magnificent. This sense of awe, triggered by contemplating such a profound mystery, is far more than just a fleeting feeling of amazement. Scientific studies have begun to quantify its incredible benefits for our mental and emotional well-being. Researchers in the fields of psychology and neuroscience have found that regularly experiencing feelings of awe, whether by gazing at a starry night sky, standing before a grand mountain range, or simply learning about a cosmic enigma like this one, can have a measurable, positive impact on our health. It can significantly lower stress levels by reducing the production of cytokines, those inflammatory proteins that are linked to chronic stress and anxiety. It literally shifts our perspective, causing us to feel smaller in the best possible way, making our personal worries and daily irritations seem less significant when viewed against the backdrop of the infinite cosmos. This isn't about diminishing our problems, but about contextualizing them within a grander narrative, which can be an incredibly liberating and therapeutic experience. In a world that often feels overwhelmingly fast-paced, demanding, and focused on the immediate, the intergalactic glow offers a form of mental escape that is both healthy and empowering. It invites us to engage in what psychologists call self-distancing, a cognitive shift where we step back from our own narrow viewpoint and adopt a much broader, more objective perspective. Thinking about a faint light that has been traveling for billions of years from a time before our planet even existed naturally pulls us out of our own heads. That work deadline, that social drama, that nagging worry, they don't disappear, but they are temporarily resized. They become small pieces in a much larger and more fascinating puzzle, which can dramatically reduce feelings of anxiety and create a powerful sense of calm and mental spaciousness. Furthermore, this mystery actively cultivates a mindset that is essential not just for scientific discovery, but for navigating the complexities of modern life, resilience. The very act of confronting a question that has no easy answer, of sitting with uncertainty and not turning away in frustration, is a powerful exercise in cognitive flexibility. It teaches us that not all problems have immediate solutions, and that the process of questioning, of exploring, of collaborating with others to chip away at a problem is itself a worthy and rewarding pursuit. This builds intellectual and emotional grit. It encourages patience, humility, and a willingness to embrace the unknown rather than fear it, a quality that is invaluable in our personal lives, our careers, and our ever-changing world. The pursuit of this cosmic secret, therefore, is a quiet training ground for the human spirit, strengthening our capacity to face other, more earthly uncertainties with greater courage and adaptability. Ultimately, the psychological power of this mystery lies in its ability to reconnect us with a sense of meaning that transcends the everyday. It sparks a childlike wonder that many of us lose touch with as adults, reawakening that fundamental urge to ask why and how without any expectation of a quick reward. This engagement is a form of active meditation, a focus of mental energy on something expansive and positive. It fosters a deep sense of connection, not just to the global community of scientists and enthusiasts also captivated by the question, but to the cosmos itself. We are not passive observers of a static universe. We are conscious participants in an ongoing, dynamic story of discovery. This realization that we are part of a species that can look into the void, see a glimmer of something inexplicable, and dedicate itself to understanding it, is perhaps the most uplifting and psychologically enriching aspect of all. It affirms our place not at the center of the universe, but as a curious and integral part of its magnificent, unfolding mystery. This faint, pervasive glow between the galaxies does more than just baffle astronomers. It ignites the imagination of storytellers, providing a scientifically grounded springboard into the realms of science fiction. For decades, the concept of unexplained light in the cosmos has been a powerful narrative engine, from the mysterious monoliths in Arthur C. Clarke's 2001 A Space Odyssey to the haunting celestial phenomena in films like Contact and Interstellar. These stories tap into a deep-seated human curiosity about the unknown, and the very real discovery of the intergalactic background light pours high-octane fuel onto that creative fire. It offers a tantalizing premise that is no longer pure speculation. What if the light we're seeing is a beacon, a remnant of a long-dead civilization, or the signature of a higher dimensional structure brushing against our own? This real-world mystery provides a foundation of plausibility that makes the science fiction it inspires feel more urgent and more chillingly possible, blurring the line between tomorrow's headline and today's fantasy. This relationship between discovery and storytelling is a vibrant two-way street, a continuous feedback loop that profoundly benefits both science and the public. When a groundbreaking scientific finding like this captures media attention, it does more than just report news. It translates complex, data-driven research into a narrative that resonates on a human level. A newspaper article or a documentary about the intergalactic glow isn't just listing facts. It's framing a mystery, introducing the detectives, and inviting the audience to wonder about the solution. This widespread coverage generates something invaluable: a public engagement. It transforms abstract astrophysics into a shared cultural conversation, fostering a sense of wonder and support that translates into everything from educational pursuits to crucial funding for future missions. The public, captivated by the mystery, becomes a stakeholder in the search for answers, proving that a story well told can be one of science's most powerful allies. By examining how this specific topic is portrayed in popular culture, we see a fascinating process of translation and enrichment. A science fiction author might take the core concept light with no source and explore its philosophical implications. What does it mean for humanity if the universe is fundamentally different than we thought? A filmmaker might visualize it not as a uniform glow, but as a swirling, ethereal nebula, using breathtaking special effects to make the intangible feel visceral and immediate. These creative interpretations don't distort the science, they amplify it, packaging the core wonder of the discovery in a form that is emotionally accessible and deeply engaging. They ask the what-if questions that strict data analysis cannot, pushing the boundaries of the concept and, in doing so, often inspiring the next generation of scientists to think more creatively about the problems they are trying to solve. This dynamic is essential for making the most complex ideas in cosmology accessible to a broad audience. The mathematics behind measuring the cosmic optical background is incredibly daunting, a fortress of integrals and algorithms that few can penetrate. But a compelling scene in a movie where characters stare at a view screen filled with an impossible light that anyone can understand, that image conveys the awe, the mystery, and the profound implications instantly and wordlessly. It serves as a gateway, a hook that can pull someone in and make them want to learn more about the real science behind the fiction. This synergy ensures that humanity's greatest questions aren't locked away in academic journals, but are instead woven into the very fabric of our culture, inspiring artists, scientists, and dreamers alike to keep looking up and wondering what else is out there, shining in the darkness. But as we reach ever further into the cosmos with our technology, we must also look back at the trail we're leaving behind. The quest to solve mysteries like the intergalactic glow doesn't happen in a vacuum. It's part of humanity's larger, accelerating push into space, and that expansion brings with it a crucial responsibility. Every new telescope we launch, every probe we send to a distant world, adds to the growing complexity of our orbital environment. We are now facing a pressing issue of sustainability, where our desire to unlock the universe's secrets must be carefully balanced with our duty to preserve the space around our planet for future generations. The very tools we use to gaze into the deep, pristine darkness are beginning to cloud our own near-Earth skies. The most visible symptom of this challenge is the rapidly growing cloud of space debris encircling our planet. This isn't just about a few discarded rocket boosters. It's a cascading problem comprising millions of fragments, from defunct satellites and spent stages to tiny flakes of paint, all whipping around Earth at breathtaking speeds of over 17,000 miles per hour. Each piece, no matter how small, becomes a hypervelocity projectile capable of catastrophic damage. This growing shell of junk poses a direct threat to the International Space Station, operational satellites that provide critical services like weather forecasting and global communications, and even the very space telescopes we rely on for discoveries. The situation is so concerning that scientists are actively developing new missions specifically designed for space trash removal, testing nets, harpoons, and magnetic systems to capture and deorbit this hazardous material. It's a stark reminder that our celestial backyard requires the same careful stewardship as our forests and oceans. This dilemma directly impacts the future of astronomy and our ability to study faint phenomena like the intergalactic glow. The dream of building even larger and more powerful space telescopes, positioned in stable orbits a million miles from Earth, must now be weighed against the long-term cost of getting them there. Every launch carries a risk of adding to the debris problem through accidental explosions or collisions. Furthermore, the skyrocketing number of commercial satellite constellations designed to provide global internet coverage is already creating a new headache for ground-based astronomers. The trails of these bright, low-orbiting satellites are increasingly photobombing the long-exposure images taken by the world's most powerful observatories, streaking across the data and potentially obscuring the very faint signals we're desperate to detect. The darkness we seek to study is literally being polluted by our own technological ambition. Confronting this challenge forces a fundamental shift in how we approach space exploration. It calls for a new ethos of ethical spacefaring, where every mission from its inception is designed with a full life cycle plan that includes responsible disposal. This means building future telescopes and satellites with built-in propulsion for controlled deorbiting at the end of their lives, guiding them to burn up safely in the atmosphere or sending them to a distant graveyard orbit. It involves designing hardware that minimizes the risk of fragmentation and pioneering new, cleaner propulsion technologies. This holistic approach transforms astronomy from a purely discovery-driven field into one that also practices planetary and orbital stewardship, recognizing that our right to explore is inextricably linked to our responsibility to preserve. The greatest discovery we could make might not be about the distant cosmos, but about learning how to sustainably and respectfully become a spacefaring civilization, ensuring that the windows to the universe remain clear for all who look up after us. In a world that often feels increasingly fragmented, where differences in opinion and background can create deep divides, it is remarkable to see how a single, profound mystery from the depths of space can bring us all together. The enigma of the intergalactic glow has become a powerful unifying force, a shared question mark in the sky that draws people from every conceivable walk of life into a single, awe-struck conversation. This isn't a puzzle just for astrophysicists in their labs. It is a cosmic story that resonates with the artist trying to capture its ethereal beauty on canvas, the educator using it to spark a student's lifelong passion for science, and the everyday person who simply looks up at the night sky and feels a deep, innate curiosity about our universe. It transcends language, culture, and discipline, reminding us that beneath all our surface-level differences, we are all human beings sharing the same small planet, gazing out at the same immense cosmos and wondering what it all means. This collective engagement creates a unique and powerful form of common ground, especially during times of societal division and conflict, when our attention is focused on a mystery that is billions of years old and billions of light years away. The things that separate us can suddenly seem much smaller. Political disagreements, ideological battles, and cultural differences don't disappear, but they are temporarily put into a much larger, more humbling perspective. Discussing the possible origins of this light becomes a neutral territory, a collaborative space where the only thing that matters is the shared pursuit of understanding. Online forums light up with conversations between experts and amateurs. Social media platforms host vibrant debates between theorists and observers, and local astronomy clubs see renewed interest from people of all ages, all drawn in by the captivating allure of a question that no one on Earth can yet answer. This mystery provides a rare and precious opportunity for us to practice working together, to value diverse perspectives, and to remember that some endeavors are simply too grand for any one group to tackle alone. Ultimately, this shared fascination connects us to a timeless human tradition that stretches back to our earliest ancestors. The impulse to look up at the heavens and tell stories about the lights we see there is one of the most ancient and universal parts of the human experience. From the campfires of prehistoric societies to the high-tech control rooms of modern space agencies, the drive to understand our place in the cosmos has always been a fundamental part of who we are. By engaging with this mystery, whether by reading an article, watching a documentary, or simply pointing out a dark patch of sky to a friend, we are participating in that grand, ongoing narrative. We are adding our own chapter to the human story of exploration, becoming part of a chain of curiosity that links the past, present, and future. This unifying power is perhaps the most beautiful and unexpected consequence of the light that shouldn't exist. It doesn't just challenge our models of the universe, it reaffirms our deepest human connections. This relentless pursuit of a faint whisper of light across the cosmos is so much more than just a single scientific problem. It is a living, breathing demonstration of how science actually works at its very best. We often picture discovery as a straight line, a triumphant march from a question to a definitive answer, but the reality is far messier, far more interesting, and ultimately far more powerful. Science is an endless, iterative conversation with the universe, a cycle where every tentative answer immediately spawns a dozen new, more nuanced questions. The mystery of the intergalactic glow is a perfect case study in this beautiful, frustrating, and exhilarating process. Its initial detection wasn't an ending, it was a beginning. The first measurement didn't solve anything, it simply upgraded the mystery, transforming it from a "what is that" into a far more profound "how can that possibly be?" This process is the engine of all scientific progress. It's a self-correcting mechanism built on a foundation of healthy skepticism and relentless verification. A single observation, no matter how tantalizing, is never enough. It must be confirmed, tested, and challenged from every possible angle. The teams using Hubble had to verify their findings against data from New Horizons. Theorists had to take the measured intensity of the glow and run it through every conceivable model, watching most of them fall short. This isn't a sign of weakness or failure. It is the system working exactly as designed. It is a rigorous filter that ensures only the most robust ideas survive, and in doing so, it slowly, painstakingly builds a more accurate picture of reality. The journey to understand this light has been a masterclass in this discipline, showing how collaboration and competition between researchers around the world refine raw data into genuine knowledge. What this mystery teaches us, above all, are the human virtues required for this grand endeavor: patience and perseverance. Scientific breakthroughs are rarely eureka moments. They are more like watching a photograph develop in a darkroom, slowly emerging from a blur into focus over years or even decades. Astronomers have spent the better part of 2 decades just confirming the signal exists and ruling out the simplest explanations. This requires a special kind of dedication, the willingness to devote a career to a problem that may not be solved within your lifetime, to find satisfaction in the chase itself, and in the knowledge that you have helped rule out a dead end, paving the way for those who will follow. This patient accumulation of understanding, brick by brick, is what constructs the cathedral of human knowledge. As we stand today on the precipice of new discoveries with tools like the James Webb and Roman telescopes, we do so by standing on the shoulders of all the curious minds who came before us. We honor the legacy of astronomers like Vera Rubin and Fritz Zwicky, who first grappled with the invisible components of the universe, and the engineers who turned seemingly impossible ideas into reality. The intergalactic glow is our generation's inheritance, a question passed down to us to solve with the new tools at our disposal, and we, in turn, will pass the torch, whether the answer is found or the mystery simply deepens further. This is the enduring nature of scientific inquiry, not a destination to be reached, but a perpetual and awe-inspiring journey into the unknown, a testament to our species' unyielding desire to understand the cosmos we call home. The light that shouldn't exist, this enigmatic intergalactic glow, stands as a powerful testament to the fact that our universe is far stranger and more wonderful than we ever imagined. It's a mystery that refuses to be neatly filed away, a persistent signal from the void that challenges the very foundations of our cosmic understanding. From the moment it was first detected as a stubborn, unexplainable residue in the data from our most powerful telescopes, this phenomenon has sent ripples through the entire field of cosmology, forcing us to confront the humbling reality that our map of reality is still missing entire continents. We've journeyed through the myriad theories from seas of rogue stars and countless unseen dwarf galaxies to the breathtaking possibility that we are witnessing the slow decay of dark matter itself. Each hypothesis opens a new door, only to reveal a longer corridor filled with even more questions, connecting this single anomaly to the biggest puzzles we have: the nature of dark matter, the timeline of the early universe, and the fundamental laws governing reality itself. Yet, the true value of this mystery may not lie in its ultimate solution, but in the magnificent journey of inquiry it has ignited. The pursuit of this faint light has driven technological marvels from the Hubble Space Telescope to the James Webb, pushing the boundaries of engineering and data analysis. It has fostered unprecedented global collaboration, uniting scientists across borders in a shared human quest for understanding. It has inspired public wonder and engaged citizen scientists, reminding us that the cosmos belongs to everyone. This process, the collective effort to shine a light on the darkness, is a beautiful expression of our species' insatiable curiosity and our refusal to accept easy answers. It enriches us not just with potential knowledge, but with the virtues of patience, collaboration, and the courage to question everything we think we know. So as we stand here on our tiny, pale blue dot, looking out into the immense and whispering darkness, let this mystery be a reminder. The universe is not a puzzle to be solved, but a story to be explored, and we are all part of its unfolding narrative. Stay curious, keep looking up, and never stop asking the big questions. Who knows, the next great discovery, the one that finally illuminates the darkness, might just begin with you. Share your own thoughts and theories down in the comments below, and if you've enjoyed this deep dive into the cosmos's deepest secrets, make sure to subscribe and hit the bell so you don't